If you haven't broken any important, expensive equipment, you have not been taking enough risks. In order to make a discovery, you have to have 1,000 failed discoveries for every one discovery that works out. I have to confess, my ambition is not just to invent something that somebody uses, but to invent something that everybody uses every day.
The 632 Nanometer podcast team visited Professor Eli Yablonovich's office at UC Berkeley for a marathon discussion. Eli's pioneering work underpins the technologies we use every day. They cover the details behind his inventions, as well as his unique career spanning academia, industrial research labs, and startups. In Eli's own words, "My goal was to make something most people use every day, and I have been lucky to do that more than once."
Was there, in your time, any person whom you would admire, or was there any type of the model, or a person whom would you like to go to the talks and learn something?
Well, I wish I could go to talks from Thomas Edison. I think he was the closest I had to a hero. But now that I've learned more about Thomas Edison, I realize he didn't really know that much and was very intuitive, and also had one great idea, is that in order to make a discovery, you have to have 1,000 failed discoveries for every one discovery that works out. And he was very prolific that way. He tried many different things, and that was responsible for much of his success.
Was it one of his inventions which inspired you to come to this world of science and engineering, or was it something else?
I think it's just all the things that we relied upon were things that originated with him, including the electricity system, the utilities, the sound, the recording. We're recording. He's the father of recording. He's the father of the motion picture camera. So he did a great many things. And now in hindsight, I realized they were sort of mechanical things and not really physics oriented. So obviously, my opinions evolved a little bit over time.
Well, what brought you to science? Like how did you decide to go into that direction?
It's very simple. I was 11 years old, and the Sputnik was launched. And my mother is from the Soviet Union, and a great lover of Russian culture. And I remember my parents were discussing in the living room in a very worried way, what does this mean? And they were very worried. They had escaped from the Soviet Union, and they were very worried that the Soviets had placed a satellite into space. And I said to myself, I was a child, and I said, this must be very important. So I became very interested in science right at that point.
Did you go towards the astrophysics direction, or make aerospace?
No, it was whatever we could do with the things that we scrounged together as children and as teenagers. I would go to the garbage of the radio repair shop and find components and things of that sort.
It's kind of funny because now everything's so miniaturized that it's actually tough to find something that you can take apart where you can tell what's going on in there. I mean, people replace like phone screens or whatever, but you can't really pull apart the
That's right. It's a shame. I think my generation, we had that experience, and I don't know how to replace it for the younger generation.
There's like one guy who posts a lot on Twitter about this. I think he now has a startup, but he built a whole fab in his basement. You know, it's like he's like an 18-year-old who just started building, and electron microscope, eventually started doing deposition, started making transistors smaller and smaller and so on. But yeah, it's not as you have to get down to the level where things get interesting. It's tough these days.
Right. It's in those days. I think one of the things that influenced me, I was influenced all along, and then I submitted a science fair project. And I had a partner, and it cost $20 for all the scientific equipment, the materials, everything cost $20. And then we showed up to the science fair, and we realized we needed a poster board, we needed display things. Okay, it's another $20. And so you could do science for very little money back then, and although the dollar was worth a lot.
And by the time you were in your PhD, who was kind of the person in your fields that was doing research at the time that was coming up with, like, what was at the edge of the field at the time you were doing your PhD?
Of course, I have great respect for my thesis advisor, Nicholas Bloombergen, but he was a very balanced figure in the sense that he had to run the group, couldn't put up with a lot of philosophical nonsense. I would try to talk to him about the philosophy of physics, and he wasn't interested in that at all. And so he was just very businesslike in that respect.
Could you share a little bit more about your PhD time? So we found that your PhD thesis title was Nonlinear optics with CO2 lasers.
Yes, the CO2, yeah. At the time when I entered graduate school, the pulse CO2 laser had been invented, was called a T laser, transverse electric excitation laser. And it was something rather new, and I couldn't resist, so I made one. They were very easy to make.
How do you make a pulse CO2 laser?
Okay, well, it's you just make sparks. So you have the right mixture of gases, CO2 and helium and so forth, and you make a spark, and to keep the spark under control, you have a resistor, and then you have a plastic tube that has 1,000 resistors stuck in. You get 1,000 sparks, and it's about 1 meter long, and maybe 2 meters long, and then you just make the sparks, and it lasers. It was quite amazing, quite a remarkable thing. And of course, later on, people made much more exotic and interesting forms of CO2 laser. And now we have many types of lasers that are working on surprising mechanisms and don't look at all like a normal laser.
Anything challenging? What was the most challenging in your PhD project when you constructed those lasers?
I think, honestly, I got here because nothing was challenging in my PhD. I had that because I had, as a child, been doing all these experiments. I was very advantaged. I had a gift for experimental work, and so whenever there was an obstacle, I could overcome it. I can tell you one thing that's interesting, and that I pass on to my students today. If you haven't broken any important, expensive equipment, you have not been taking enough risks. You need to take the risks.
Push us to the very limits.
You have to break things. And so that I had no guilty conscience when things broke.
I think in general, that's probably like also one of your talents in terms of science. So I could see you usually go ahead of others while there is still an area to explore before everyone else jumps in. So there is not much of the competition for.
Yes, I think it's very important, and this is a big problem we have with young people. We put so much pressure on them, and they should be given enough space to take scientific risks. Go into something that may not work out, and it's very hard to do that. As a thesis advisor, I have to give my students something that is pretty guaranteed to work, and I prefer, actually, for myself, that I would take big risks and maybe nothing will come of it. But that's how you make big discoveries.
So how long does it take for other people to recognize that this direction is worth pursuing? So when you started, there's like no one else in the field, but then later.
Well, I think in some cases I do something that looks totally obvious to me, and I have a very difficult time persuading others that this is worthwhile. And sometimes it takes a long time for it to achieve acceptance. And I can mention some examples. The idea of a photonic bandgap, that took quite a few years to reach acceptance. And I could also mention the strained semiconductor laser. The reaction, I would go to growers and say, why don't you try this? This is going to really help the lasers. And they would be growing the material. So it's a big commitment on their part. And they would say, oh, strain, are you crazy? I don't want to ruin my lasers. And so it was it was hard to persuade them. It took that one took 7 years to persuade them that actually if you strain it, it will actually be more reliable and work much better.
So that's interesting. So you had the theory, but you couldn't get time on the machine or something like that to,
I think,
force your way into like
in reality
or something.
It's a whole scientific enterprise. I can do a little bit,
yeah,
and then I have to persuade others to take it to the next step. And even let's say you're doing only theory, you need the other theorists to accept it and to build on it. And so that's a problem in all of science, is that we need to be persuasive to have influence. And if you don't persuade anyone, then it's like nothing had been accomplished. It's also the reason why the funding agencies are very happy about publication and about support for journals. Because if you haven't told what you've done and spread the word out, that's the last stage of scientific accomplishment, is to tell everyone.
Yeah, I guess one thing we were kind of curious about is when you were starting out, you ended up working at Harvard for a while, and then you pretty quickly went to Exxon, which is I don't know if at the time that was a typical track or that was like a big jump.
Actually, I had been at Bell Labs, then I went to Harvard, and but it's very hard to get tenure at Harvard. So I wasn't going to get tenure, and I said, well, to hell with that. And I didn't really want to join any other university. And at that time, it was the period around the second energy crisis, and I like to go into an area of research where not very much is known. And one way I could tell, I could go to people who were experts and say, "Can you explain the solar cell to me?" And I had great difficulty getting an explanation. In fact, I decided it must be a good field because nobody seems to understand anything. And I've done that a few times. I think that's very important. Of course, if you go into a field where nobody understands anything, maybe you won't understand anything either. And so there's that risk. But that's a risk that I've been willing to take.
So at the time, people hadn't been interested in solar panels really until the energy crisis. And there was a peak of interest, but very little, the
scientific knowledge was at best incomplete. And I have a certain level of a standard. When can you say you understand something? And I wasn't getting that from the explanations that people were giving me. So Jimmy Carter was very worried about the energy crisis and worried about being reelected. And one of the great political events of the late 1970s is he gave a presidential speech wearing a sweater and encouraging everyone to turn their thermostat down in the wintertime and to wear sweaters. And so that didn't look that great, and he ended up losing the election. But everybody could immediately understand that energy was a big problem. And I became very interested in energy. Even before that, I was interested in energy. And so it seemed like, okay, I will go to Exxon and I will figure out how solar cells work and will make a big difference and so forth.
Was Exxon genuinely motivated to?
Yes, Exxon at that time had the largest solar cell company in the world.
Oh, wow.
Which was located in Massachusetts, not very far from where Mikhail comes from. And of course, in those days, to have the biggest solar cell company in the world was not a very big factory. But still, they were the biggest, and they were doing basic research on solar cells. There was a group. There were people I could talk to. I had a mentor. So I should mention about mentors. I was very lucky that I had as a mentor a gentleman who should be better known. His name is Al Rose, and he was a great leader at the RCA laboratories. And probably the two of you are too young to know anything about RCA, but RCA created radio.
Well, they created the RCA clean. That's the one. That's the most important thing I know.
You should know a few other things. They were the pioneers of radio. They were the pioneers of commercials on radio. So they were making it was born after World War I.
Well, that's an incredible dynamic range. They figured out commercials and how to, clean.
They had a great leader, David Sarnoff, and they put him in charge. It was actually, it's a very long story having to do with the origins of RCA. It's a very interesting story, but I'm going to skip that. But just to say that RCA created radio, it created commercials on radio to pay for everything, and they were making so much money selling the hardware and selling the commercial time that already in 1926, David Sarnoff said, the government's going to come after us. We're making much too much money. We're much too successful. And so he put all the efforts into basic research. And in 1926, he decided to concentrate or put the research lab onto television. And they created television starting in 1926. And one of his first acts was to ask around who can be the leader of the television research effort. And he found that there was one person, Vladimir Zworykin, who came from the St. Petersburg Institute of Technology, where his thesis advisor told him in 1905, radio is done, we have to do the next thing, television. And so between 1905 and 1910, Vladimir was working on television, all the different concepts. And then he was wise enough to get out of Europe before World War I, ended up working at Westinghouse as a research scientist. And then Vladimir Zworykin gave him an unlimited budget, create television. And he did. And one of the people he hired was Al Rose. And Al Rose was in his 70s when I was maybe 30. And he was a wonderful person. He knew everybody and knew all the old technologies and how they were developed, and taught me a lot about. He was also very interested in solar energy. He was interested in television and vision, things of that sort. So he was very much a generalist, and he could talk about different things. I'll mention one of the things that he taught me very early on. So people, I tell them that, well, I was very lucky. But every other day I would have lunch with Al Rose, and people admire that tremendously. But these are the older generation who know what a charming gentleman he was.
Mm-hmm. Wow, that's really amazing to have such a great mentor. So Rose,
and then Al Rose was at Exxon. Sorry.
Yes, he had RCA had fallen apart. It had fallen apart for a specific scientific reason, and that is that there were companies in Japan that made better phosphors, better inorganic phosphors for the cathode ray tubes. And so you would go to the store and you would see an RCA television next to a Sony television, and the red was much redder in the Sony television. It destroyed RCA overnight, and the lab, everything fell apart. And so he became a consultant on the photovoltaics at Exxon. And I had the privilege of working with him for a 5-year period, which was quite amazing time.
So when you were at the Exxon Research Center working on the solar cells, what were the main challenges, or what was the main task people would look into? Because we know that, for example, one of your major outcomes is related to the Yablonovitch limits of the light trapping in the that's like a single layer or general any layer.
Yes,
solar cell.
Yes, I went there and I tried to learn about solar cells, and I was rather shocked that they weren't doing the most obvious thing. And so the most obvious thing was that the solar cells were taking a light ray into the solar cell, and then it would just go through the solar cell and you'd get a single pass. And I was rewarded because I said, no, the single pass is not a smart way to do things, and there are easy ways to have multipass of the light rays. And so I went and I did a calculation, and you see here that there are some shapes. If you think about the shape of the solar cell or the shape of the silicon, there are some shapes where you have a single pass. So you have, for example, the light goes into a solar cell, goes back out again. You get the benefit only of a single pass, but if you have a parallelogram, the same thing, a single pass. And even if you have a sphere, if you have an angle of refraction going in, you'd have the same angle of refraction going out. And so again, you would have only a single pass. And this is to be contrasted with other geometrical shapes that are very different. For example, I have here a trapezoid. If the light goes in, it can reflect once, bounce around, and after it bounces a few times, it has no memory of the original angle, and it can fill the internal angle space. And and the same is true for a racetrack shape. And almost all shapes have the property that the light rays become randomized in direction. And so this reminded me of something I had in graduate school, which I never fully understood, which is when do you have non-ergodic behavior versus ergodic behavior? And I have to admit, I didn't understand it fully when I was in graduate school, and the concept of being ergodic, but now we reduce it to children's shapes. They get blocks, they get shapes, And you don't ask this to your kindergartner, but some of the blocks will be non-ergodic and some of them will be ergodic. And the ones that are very simple, like rectangles and parallelograms and spheres, you'll only get a benefit of a single pass of the light ray. Whereas if you have a slightly more complicated shape, like a trapezoid or more of a racetrack shape, the light rays will bounce in and they will bounce over and over and over again.
I have a question. Why there are no reflections shown in the simple shapes, but you could imagine like a reflection in the rectangle or something like that.
Let me explain about reflection. Say this is a semiconductor for a solar cell. Then the refractive index is very high. And this is not a refractive index that other people are accustomed to. So the refractive index of most semiconductors is somewhere around 3.5. And so you get total internal reflection. And in fact, that turns out to be very important. You get total internal reflection, but there are rare examples where you don't get total internal reflection. And that is because of the very large refractive index. You have to come almost normal to the surface to be able to escape. So it's very hard to escape. And then if you calculate, okay, what is the solid angle that escapes from internally, from inside a solar cell or any semiconductor? It represents a 15-degree cone. So it's a very narrow cone, and you have to compare it with the 4 pi radians, the full angle space. And so you do that, and it works out that that little escape cone, that tiny escape cone, turns out to be 1/4n² of 4 pi radians. And that seems like it's of order unity, right? N is of order unity, 4 is of order unity, okay. But it's not, because n is very high. It's 3.5. And so square it, it's 12. And multiply by 4, it's 50. So only 2% of the light is escaped. The rest of the light, you can guarantee, is going to be reflected, but only for the ergodic cases. For the sphere and the rectangle, if it goes in, it comes back out again. Guaranteed. There's no reflection at all. And so what this leads to is that you can build up an intensity inside the photovoltaic cell that is 50 times greater than the incoming sunlight. So this dawned on me, and nobody had realized that the effect could be that big. And I can give one more example of this effect. Suppose you're standing at a window and the sun is shining in. You say, inside the glass, what intensity of sunlight do you have inside the glass of the window? You have, well, one sun is coming in, okay? But if you take a piece of glass that has some irregular shape to it, and I'm thinking of sculptured glass, like sometimes roughened, for example, the easiest thing to do is to make it rough. But let's talk about sculptured glass. And that sculptured glass, just standing out in the sunlight, is surprisingly going to have 4n² higher light intensity than one sun. It'll be very intense sunlight just inside the glass without any particular effort. So it's a totally passive mechanism, and was not understood and not appreciated. And that also took a while to become accepted by the people who make solar panels. But there are a small number of people at that time who were experts on solar cells, and they grasped it right away. Okay, and they started publishing papers on it. But to get it accepted by the industry, they said, "Oh, you're making the surface rough. Is that so you could, is that like an anti-reflection coating, so you can have multiple scattering and multiple reflection?" I said, no, it has nothing to do with anti-reflection coating. It has to do with light trapping. And so that took maybe 15 years to be adopted by industry. And now it's been adopted. Of course, now there's a field, and many people write papers on this, and I can't tell you how many papers have been written claiming to exceed the 4n² limit. But there's always a catch in those cases. But what happened is that it was accepted by industry in the late 1990s, which was over 15 years after I originally published the paper. But since that time, every solar panel has light trapping built into it. And so I'm proud of that as a kind of like something I was going against the accepted wisdom, and it worked out.
So I understand this is the case of bulk material slab where you can engineer the surface, and so it's like proportional to this n square. Is it possible to go beyond this limit somehow by engineering the surface, or the maybe for physicists there's like, even though it's proportional to like n square, which is the density of states, are there ways to beat the Yablonovitch limit?
People started noticing this. So I had figured out the 4n squared, as you point out. The way I figured it out is using statistical mechanics. How many modes you have, equal probability in each mode, etc. All the things that we learn in statistical mechanics. So it was not something that came out of geometrical optics, although it could be derived that way as well. And so it became, so I told my management, and they got interested in this and so forth. And then they had a review of the research in the lab. And then some of the other research scientists said, well, that's good, but we can do better, okay? And they explained how they could do better. And I was getting a little angry at this, but I kept it in. And I was trying to say, how do I explain to them that this is statistical mechanics and you can't beat this, okay? And so I raised the question. I said, well, this is very good. And if your concept works, congratulations, you can make a perpetual motion machine because you're defying statistical mechanics. And that is the worst insult you can give people in an energy company, is that they have come up with a way of making a perpetual motion machine. So they got the idea from that, is that you have to be a little more careful in claiming that you can beat the 4n squared limit. And but there have been there are exceptions and so forth, but basically that limit is what goes into solar panels.
So what, in the end, it's something like 30%. The limit is 30%, like total efficiency, right? But is that more related to, the spectrum of the sun? Like, for example, if you have a single wavelength source, would that, what's the physical limit for that, or whatever?
Yes, it's mostly related to this. The infrared rays are too small. Those photons are too small to be absorbed in a semiconductor, and some of the photons are much bigger than the band gap, and that energy gets wasted. And that was the original concept that Shockley had, and it gave rise to the efficiency limit, and a very famous important limit in solar cells called the Shockley-Queisser limit. And but the Shockley-Queisser limit did not, it assumed a step function at the band edge, and band edges don't really have step functions. So it gets a little bit more complicated, and the story goes on. But I could spend this whole many hours talking about solar cells, but I think we need to move on.
So wait, so we left off at Exxon, right?
Yeah.
I still have more questions about that.
Yeah, okay, go ahead.
So in the end, so you developed this limit, which turned out to be significant over time. It turned out to be the limit that people use, or one of the main ones to think about solar cells. And you said that it took a while for the manufacturers, people practically making solar cells, to adopt like the surface roughness.
Yeah, which was the easiest thing in the world to do, because the semiconductor wafers are cut with a saw and they're already rough.
They're already rough. They have to be smoothed, right?
Yeah. In fact, I remember going to a trade show around 2000, and I walked into the trade show, and there was a company just selling the equipment for texturizing the surface of the silicon. And then the idea had arrived.
So my question is this:
Yeah.
What kind of gains did they see? So practically, like, what kind of gains did they see from going to a textured surface in the end?
So the gain, there was a gain in efficiency. Let me put it this way: if you can absorb the same amount of light, but you can make it 50 times thinner, then that has a very big effect
on cost.
Because the semiconductors are expensive.
Of course.
Okay, so that's a rather big impact. Then there's a second impact that is a little more physics oriented, and the second impact is because you have a greater concentration. that means you have greater free energy. Everything in the world, if it's more concentrated, it has greater free energy. This is true for chemicals. It's true for sunlight, and ended up
Just because less entropy.
Yeah, there's less entropy, and so you have greater free energy, and so it ends up boosting the voltage in the solar cells by about 1/10 of a volt. And this is kind of shocking. And it really didn't reach its fruition until the past decade at my startup company, which was called Alta Devices, where they were not actually looking for this, but it fell into their lap that they were getting much higher voltage than anyone had ever achieved in a gallium arsenide solar cell. And I told them, I think I know what's causing this. And why don't you just put a better mirror on the back? And they kept improving the mirror. They kept breaking their own record. So they established the world record for flat plate solar cells, breaking it by a huge amount because it was a new scientific concept to use the concentration of the light, to use that to have greater free energy. It translates to greater voltage. And they broke the world record by a huge amount. Normally, this is like the 4-minute mile, and if you beat it by 1/10 of a second. They broke the world record by 3 or 4%. Then that was in 2011, and then they would have.
This is 3 or 4%. You mean absolute percentages, not the percent of the.
That's right.
Like going from 20 to 23.
It went from 25, which a record that stood unchanged for 20 years, and then we took it to 27.6, 28, and very quickly to the new world record, 29.1% efficiency. So it essentially jumped 4% from 25% to 29% over a very short period of time. And it's not because we made things slightly better. We introduced a new physics concept into it, and that had to do with the management of the light inside the solar cell. So it gave rise to a slogan, which I like the slogan, is a great solar cell should also be a great LED. And what that means is that if the solar cell is really working correctly, you're going to build up a tremendous internal photon gas in the solar cell that would actually be 40 or 50 suns internal in the solar cell, just from being exposed to ordinary sunlight. And so that resulted in breaking the world record. And every new world record since 2011 is my company, Alta Devices, breaking its own record. Okay, and so I think it's become recognized that this is the way to think about solar cells in the future.
So let me just, maybe it's my ignorance, but okay, so there's a lot of light trapped in the thin film of the solar, in the film of the solar panel, 50 suns, whatever it is. Why does that make it what does it mean it's a good LED? Like, what's the connection between those things?
If you have a tremendous amount of light trapped internally, it's also going to come out, and it'll work efficiently as an LED.
It's like a resonator, basically. So it's also
it's maybe not exactly a resonator because it has to do with statistical mechanics.
Okay.
And so this part is actually rather hard to explain. And even if I had a blackboard and everything, I would still have great difficulty explaining this. But it's very counterintuitive that the purpose of a solar cell should be to take light in. Why should it give any light back? Okay, and in fact, when it's operating perfectly, it's actually giving 2% of the sunlight back. And if it fails to give that back, that means that there's something wrong, and that some of the sunlight is being wasted. And the penalty is not just wasting the sunlight, but you're also wasting the voltage.
And are you returning that 2% in the broad spectrum, or at how does that work?
It's returned at the band edge. It's luminescence at the band edge, like an LED.
Okay, I see.
That's the slogan. A great solar cell has to be a great LED. And so you should be returning 2% of one sun, which is, even though it's a narrow spectrum, it's still a lot of light.
Okay.
And if you're able to achieve that, you will reach the theoretical limits. So the way it works is that all the solar cells until 2011 they, as LEDs, they were like 10 to minus 5 efficiency, etc. The very best solar cells might have had close to 1% efficiency of that order. And then we started getting these incredibly high voltages, and it was the luminescence. We would measure the luminescence and light output, and it's 5% efficiency. Oh, nobody's ever had 5% luminescence efficiency, and that translates to higher voltage. You still get the full current, but the voltage is penalized.
So I have a stupid question. How do you measure the luminescence if you're shining light on the solar panel? How do you know it's not reflection or something else?
Right. Of course, the experimentalists have to do it carefully. There are a number of ways of doing it. You can, of course, just treat it as an LED and put in electricity and see how much light you're getting out relative to the electricity put in.
Or in the reverse way.
In the reverse way?
Yeah.
You apply
the voltage.
Yes, that's an LED. You run it as an LED. That's exactly right. And but there's a simpler way to do it where you don't have to deal with electricity. Is you could pump it at let's say at a blue wavelength, and then look at the luminescence at the bandage at a red wavelength or an infrared wavelength. And so that's a little bit easier to do. So that's normally how it's done. And so it's the easiest experiment in the world, and you can get a result immediately. And so what happens in a company, what you would do is you would grow some solar cell material. Now, processing it into a record-breaking solar cell is a whole lot of steps and a lot of work. They would never do that. What they would do is they would check to see how good the material is first. They could do this without contacts, without processing. They would just measure the luminescence efficiency. And they would say, oh, wow, this is a good one. We have a luminescence efficiency, let's say 16%. And maybe that was good enough to break the first record. And then they improved the optics a little bit. So it's all about improving the optics. It's all about making the rear mirror more reflective. And they made the rear mirror more reflective, and they got to 30%. And then they got to 40%. Each time the voltage went up to levels that were unheard of. And the record-breaking one is 50% luminescence efficiency. As an LED, it's 50%. It's a very highly structured mirror. It's a very special mirror.
This is for thin film solar cells, because there are some other competing solutions. Maybe if you can extend to what are the state of the arts.
No, what?
PPV, microconcentrators.
Yeah, there are big problems with many of the other concepts. And so, for example, concentrators, in principle, they could work better, but you have to track the sun. And the other problem with concentrators is that you can only concentrate the light that is collimated coming directly from the sun. Well, if you're looking at the sky, at best, maybe 70% of the light is coming from the sun, and the rest of the light is coming from the rest of the sky. So you may say you have a very high efficiency, but you're not including the fact that you started out throwing away 30% of the sunlight that's coming from all the other angles. So all of the exotic ideas end up having pitfalls of that sort. And one of the things that was published by the Department of Energy, for every important city in the United States, they supply an answer to a very important question. How much of the sunlight is coming directly from the sun, and how much of it is coming from directly from the rest of the sky? And for Boston and New York, it's 40% of light comes from the rest of the sky, because on many days it's cloudy.
Yep.
Okay. And here in San Francisco, it's sunny California, it's 70% of light is coming directly from the sun, but then you're throwing away 30% of the light. And then you go to the high desert. You go someplace in the desert. This is a city you never heard of, because it's a tiny place somewhere in the desert, and they have a table for that. And there is one city in the desert in the United States where 80% of the light is coming directly from the sun, and 20% is from the rest of the sky. But it doesn't, in my view, it does not constitute a record, because you've thrown away 20% of the light.
That's really interesting. But
there are many little pitfalls like that are just bookkeeping things that are not physics. In solar cells. But many of the things you hear about in solar cells, unfortunately, are scientifically incorrect. And it's just, I was going to write a book on solar cells. I might still write a book, but it's hard to keep up with every idea that needs to be corrected.
Well, that immediately brings a question to mind of like, what are the biggest kind of like poorly understood things in solar cells? But I guess I was just going to ask you. So the classic solar cell, the one that's kind of, if you order a solar panel, you get the normal bulk solar cell. Does that benefit in any way from these ideas? Like, have those solar cells need to be thin film to benefit from this type?
No, those ideas work whether it's a thin film or thick film. But one of the goals is to, since the material is rather precious and expensive,
is always to decrease the thickness.
To decrease the thickness. And this whole idea that you need to have a earth abundant element is also an incorrect idea. The reason is that we can make solar cells that are extraordinarily thin. We could make them of the order of 100 nanometers thick, and they could be just as efficient as a thick solar cell. When things are only 100 nanometers thick, the cost of the element is not a factor. The material cost is very modest. I don't recommend making it out of gold, but you could use just about any element. And so these are some of the misunderstandings. And it's a little bit frustrating that there's a lot of misunderstanding, and it's very hard to keep up with it.
What do you think would have to happen for silicon, like the standard silicon solar cell, to evolve to like more complex, more efficient?
The premise of my company, which Alta Devices, which did a huge amount of research, broke all the world records and so forth. The premise was that people will pay for efficiency, and we will be more efficient. And it's true. I think people will pay for efficiency, but we're living in a time when very inexpensive panels are coming from China. And so there was not much of a spirit to invest money in producing new types of more efficient panels.
Yeah, so we have to wait until that completely saturates.
Well, not really, because they're already using the light trapping idea. Just to go back to your earlier question, how much do they gain by that? They gain several absolute percent. So it takes them, let's say, from 18% to 21%. This is very typical for what light trapping can do. Allows them to make the silicon cells very thin. But the economic conditions in China are such that the manufacturing of solar cells is a jobs program. They're creating jobs for peasant farmers. And so they need to, they end up subsidizing it. So there's no point. You couldn't make a business case fighting against subsidies for make-work projects in China. Okay, I think we've spoken too much about solar panels. I know why. The physics is interesting. Every part of it is interesting. We could spend the whole afternoon talking about solar panels. Yeah. No, this is good. This is good. And
let's move on.
That's why I had this show. That this has to do with ergodicity. It had to do with
extremely
mechanics. And it took a long time for that part to be appreciated.
So then let's move to the next scientific journey. We left, and then you went to Bell Labs.
I went back to Bell Labs. I had been at Bell Labs, remember? I had been, and then I came back.
Yeah, what's the story with that? Was it, did somebody invite you back, or how did you end up back?
It was very simple. It's an oil company. And there was, at a certain point in history, there was a very enlightened management that wanted to diversify the company. And then it turned out that the diversifications didn't work out. So a new guy became chairman of the board, and he literally fired the president of Exxon, because he was chairman of the board. He fires the president of Exxon, and he says, we're an oil company now. No more solar cells.
Okay.
And so I left, and it was in New Jersey, and Bell Labs was right there. So I just switched over to Bell Labs. And I didn't want to work on solar cells anymore because it hadn't worked out. So I decided to do other things. And
it's funny that you say it hadn't worked out. You know, you ended up with like something named after you. It wasn't really working. So it's hard to know at the time.
No, when you're young, that's the reason why we put so much pressure on young scientists. I hope everything's being recorded. And this is the useful thing for the young people to know, is that we're putting too much pressure on them, and that things have to work out. It has to be a great scientific discovery. It has to be recognized right away. And so
nature.
Yeah, and going to nature, of course, I'm
get the Nobel Prize.
I'm opposed to that, and I think they should publish all over the place, and people should read it and decide for themselves if it's a good result. But maybe it's an indication that, well, I don't think it was good. It was good. It wasn't just that had set a very high scientific standard for myself. I actually lost my job. Okay.
Hmm.
Well, I didn't exactly lose my job. But they made me fire everyone who was working for me, and they provided a cash inducement if I would resign, and so forth. But it was clear that they were not interested, and so there was no point to stay there. And so I just, instead of going one way, I turned right at an intersection instead of turning left, and ended up at Bell Labs. And that was an interesting experience. The company had just split because of the antitrust. The company was broken up, and I became interested more in communications problems. And of course, I learned a lot about semiconductors during solar cells. I had started out as a nonlinear optics person, and then I became a plasma physics person, and then a solar cell person. So I was, I think that's good change. And so then telecommunications. So telecommunications, of course, the big thing was optical communications. I mentioned earlier that Bell Labs had hired 2,000 PhDs to make optical communication a reality. And so it was a good environment. A lot of people knew a lot about it, and I was in a new environment.
Maybe just for people listening to this, I think you mentioned this before when we were chatting, and it's very interesting. Like, what prompted that? So why did Bell Labs do that? What's the background?
Okay, why did Bell Labs make such a big commitment?
Yeah, how did they end up jumping in?
So part of being a monopoly and part of the reason why it was broken up is the engineers had total control over how the telephone system worked, and they had essentially an unlimited budget, which was essentially 2.75% of every telephone bill went directly to Bell Labs. So the budget was huge, and they were pursuing the things that they should pursue in their business, which is the discovery that was made in the late 1960s in England that optical fibers could have surprisingly low loss coefficient. And from that initial suggestion in England, in January of 1970, I was a graduate student, and two papers came out. One from Bell Labs, the achievement of 20 decibels per kilometer, and the same achievement from Corning Glass. And so that was regarded as fantastic because they had nothing like that. In the long distance calls, you had to have a repeater station every few miles. It's just ridiculous. Now you could go many kilometers.
And you were saying the pipe for the long distance calls, the actual coaxial cable was like as thick as your thumb.
Yes, the center conductor was as thick as your thumb. The cable itself was as the diameter of a golf ball. And so it was very clumsy technology. It was very easy to imagine we need to replace this, and so it was their business. They needed to keep up. So they recognized this would revolutionize wired communication, and so they spent whatever it cost to hire 2,000 PhDs. Cost a lot of money. And to equip them and let them do it. So I was there, and by then I understood quite a bit about semiconductors from my solar cell work, and I realized that there was something that we're doing wrong with lasers. And for that, I don't have a figure, but I can draw the figure. So one of the most important things in semiconductors is called the band structure, and it's the energy versus momentum of the electrons. This K vector is representing momentum. And so famously, the electron band, so you have the so-called conduction band, and then you have the valence band. And then something very strange happens in virtually all semiconductors, is that the valence band is mostly consisting of P wave functions. And so the P wave functions don't hop so easily from atom to atom. And so they create two bands, which are heavy holes. So you have here heavy holes and light holes. So I'm going to show them as X's. And so what happens here is that you try to get a population inversion. So you try to put electrons in the conduction band. Yeah, the X. Yeah, it's K. Okay, so okay, so then it's going to be very difficult if you're a biologist, and if you're a hydrogen physicist, it's also very difficult, and you're a software person, it's also very difficult. So you have to know about the bands in semiconductors. Okay, so this represents the momentum of the electrons, and this represents the energy of the electrons. And so you're trying to create a population inversion to make a laser. Okay. The idea is to put as many electrons up here as possible. So what you want is just to have a high density of electrons, and but it's very easy to have a high density of electrons if they're, and you need them right at the band edge. So if there are very few states at the band edge, then it's easy to fill those states and you can get a population inversion. But at the conduction band, it's very hard to fill those states because there are so many of them, because the band is very, very flat. And so the heavy hole band is a killer for semiconductor lasers. And yet this was already 1985, and the semiconductor laser, the room temperature semiconductor laser, had been in existence for about 15 years, and was the candidate to make optical communication practical, and a huge amount of work had already been done. And
what was the reason that the semiconductor laser was kind of the obvious choice for connecting it to these fibers that were going to be laid across the country and across?
Yeah, that's a very good question. The fiber is just a little tiny thing, and in order to transmit a high data rate, you need to have at least one photon for every bit. In practice, you need maybe even 1,000 photons, depends upon how efficient your system is. Even today, it takes hundreds of photons to represent a bit. And so you needed to concentrate a large amount of light into a single mode of an optical fiber. And so only a laser can do that. And you can't do that with incandescent light or other type.
What about like a different laser, just like a different, not semiconductor? Like is it because it was in the right wavelength range or the right,
well,
or
many
cheaper
reasons for it, but what the right wavelength range is one reason, but another reason, it's so cheap. You can
mass produce them.
You can buy a laser for less than $1.
Yep.
So became very, and of course these lasers had other applications in the DVD players and so forth. But let me tell you what made that possible. So what happens is that you really hate this heavy hole band. You hate it. It's causing a lot of trouble. It means you have to pump a tremendous amount of current, because the holes, you have to pull all those electrons out, and you end up having to pull a huge current to pull all those electrons out. So what you really want is for the valence band to be similar to the conduction band, which is to say, to have a very light band.
And so just to clarify, so the problem with the heavy hole band is that there are all these extra holes that you have to empty, because otherwise those will absorb photons and you won't lay.
No, it's not that they will absorb photons, is that you need to empty them in order to get a population inversion.
Right. So because otherwise, okay.
Okay. Yep. So you need to pull them out to get a population inversion. And this is, of course, what has happened in the, let's say, since the laser was invented. The semiconductor lasers have become so dominant because they're so trivial. And you ask, how do we get the holes out? You just apply a battery. You just have a current. And so nowadays, when people say a laser, they automatically assume you're talking about a semiconductor laser. And this was not true in the first decades after the laser was invented. The simplicity of the semiconductor laser is such that it's taken over most of the applications.
Maybe like for biologists, would it be possible to explain in a kinetic theory, since it's related, the band is related to the mass, so if it's heavier holes, heavier carriers, and how it's related to the threshold current?
It's a little bit hard to explain to a biologist, because it has to do with how many states there are for the holes. Then you need the density of states. And I'd love to be able to explain it to biologists.
Well, what's maybe just on a simpler level, like if so basically there what causes this band, like the dense band that has high Ks, like what's actually causing that in the crystal?
What's causing it in the crystal, and is common for most crystals, is that the valence band is the like the 2p state or the 3p state, and the conduction band is an S state. Now the p state is the electron is more confined, so it's more difficult to jump to the neighboring atoms. So it has a heavier mass, and it has a heavier mass, then there are more of them crowding into the same narrow energy region. And so you have to go right into the chemistry of the semiconductors. What is amazing about this is all semiconductors seem to have this problem. And even the gallium nitride, which has a different band structure, but the valence band has the same band structure. Once you learn the valence band, you've learned it for all semiconductors. So you have too many states you have to empty, ends up drawing too much current. You're trying to empty the states to get a population inversion. And so the solution is to have the valence band be similar to the conduction band. That is to say, have a light mass. And the way to do that, and I can show this on this sheet of paper, is that if you can somehow do something to separate these two bands so that the light band goes higher, becomes the new conduction band, how can we possibly raise the energy of the light band and leave the heavy band behind? And so this is a good spot where you want the picture.
You actually want the picture.
I want the picture for this. So what happens is that if the valence band is now consisting of the light holes, then there are not too many states here. And you can fill them with holes. Let's say for holes, I should make them empty circle. And you could fill them with holes much more easily because there simply aren't very many holes that you have to pull the electrons out of. And so if the valence band is light and the conduction band is light, it performs very well. And this was sort of an obvious idea, I thought. And I went to the people who grew the semiconductors, and there's a way to do this. And the way to separate the light holes from the heavy holes is by building in strain. And it was a time when the crystal growers were accustomed to building in some strain. And I said, build in some strain, and your lasers will perform better, and you'll become a hero. Okay. And they said, strain? Are you crazy? Strain my lasers? It's going to ruin them. They'll be less reliable because they'll be under constant stress, and so forth. So that idea was not embraced right away, and took about 7 years to become adopted. And it was adopted 7 years later, all at once, in 1993. I published it in 1985. In 1993, every laser became strained. And then there were no more papers anymore after that. There was maybe a single special issue journal, and it became the standard accepted technology at that point, into the present.
Sounds like stress is good for lasers.
So stress is good, surprisingly. They thought it would ruin the lasers, but it didn't actually make them more reliable.
What was the catalyst in 1993? Just somebody finally did it, and then everyone else?
I think somebody did it, reported good results. Then all the other growers said, hey, I can do that too. And so the problem was to persuade the first one to jump into the pool first. And that eventually took place. It was a meeting.
So maybe I missed this a little bit, but how does the strain in the crystal, why does it have that effect on the band to make it a conduction band?
The strain is breaking the symmetry.
Mm-hmm.
And if the symmetry is not broken, it's like an atom. Atoms are spherically symmetric. The semiconductor is spherically symmetric.
Mm-hmm.
And so it behaves like an atom would behave. And you'd have multiple p levels in the atom, and they would have very similar energies. But if you break the symmetry, for example, if you apply a big magnetic field, then it lifts the degeneracy. Some go up, some go down. And what's the most drastic thing you can do to a solid to lift the degeneracy? I would say strain is quite drastic. It's more drastic than an electric field. It's more drastic than a magnetic field. It's uniaxial like both. And so it lifts the degeneracy. Some levels go up. Those are the useful levels to up, and some levels go down. And so we end up with a small number of levels going up. Because it's only a small number of levels, it takes less current to pull the electrons out. And this had a very big effect on the current, the amount of current you have to pump in. And so nobody would do their lasers any other way now, because everybody wants the laser to last a long time and to perform well.
The lower the currents, the better the lifetime, because there's less heating, or
less heating, less of everything. And even worse than heating, you have excitation with free energy. It causes the atoms to move around. The crystal can actually break, or the structure changes. And so the basically this degeneracy just had to be overcome. And so I said, you can overcome it with strain. It's very easy to overcome with strain because, for example, they would grow gallium arsenide, and they would put in just a little bit of indium, maybe a few percent indium. And well, that's a bigger atom, and but it grows on the gallium arsenide, and so it ends up being strained because there's no room for the bigger atom. It only takes a few percent to do that. That was the recipe. And the strain was typically compressive strain. And when you compress something, it's actually more durable. Like, for example, rocks, if you pull on them, they break. If you push on them, they're quite strong. And so that was part of making it more reliable, less current, less heating, less excitation, and so forth. So it became totally accepted in 1993. And after that time, nobody even discussed it because it was understood all the lasers should have that property.
And just to understand, you came up with this because you had the motivation to split that band.
Yes, I had worked on solar cells. I was now working at a telecommunications company. I thought I should do something for my company. Okay, and so I figured this out, and
but the first idea was that the band needed to be split. Like that was and then it's like, okay, how do we engineer that?
Yeah, and how it was overlooked, I have no idea how it was overlooked before then. But it was a period when strain was starting to become accepted, and so I was very well aware of that. I'd been following that very closely because I'd asked myself the same question: could this be helpful for solar cells? Of course not. For solar cells, it's not helpful. But for lasers, it's very helpful. So I was in the right place.
So you had the benefit of having thought through the strain question previously for solar cells.
Yes.
Okay.
It was a time when strain was becoming slightly accepted. And so you could argue I was a prepared mind, but actually it could have been conceived 4 years earlier. By others, and they were maybe making some strained materials, but they didn't see that this would necessarily be helpful for lasers.
Actually, from that paper on, what is it, from 1986, so there's like a last paragraph about like another approach toward reducing threshold requirements might be even more successful. And then you mentioned that there is a possibility of full three-dimensional quantum confinement would make the band masses irrelevant and would put the upper and lower lasing levels on the more equal footing. Was this idea, was it successful?
What happened, this is the idea of making quantum dot lasers. And the result was 30 years of failed results. The quantum dots were not superior to the quantum wells, and but there's always a hope that it's superior for something, okay? And there are companies that are doing this, and they're trying to sell the idea that the gain material should be a quantum dot, and I think has not reached the mainstream. There are potentially some benefits, just like I said in that paragraph. There are potential benefits. Something always seems to get in the way.
So it's more of an engineering type of problem.
I would say so. For example, the quantum dots are all slightly different in size. It means if they're different in size, they come at different wavelengths. So most of them are at the wrong wavelength. Okay, because it's the lowest energy ones that are going to laze, and so I think that has been the biggest problem is the inhomogeneity.
Tuning.
The inhomogeneity, it's like inadvertent tuning, the tuning they don't want. They want them all to be identical. So this remains a very big problem in electronics today, that there are many wonderful things we can do, but we need not just good crystal quality. We actually need atomic perfection. We need to control every atom, every chemical bond, and then we can do some wonderful things. And that still eludes us, but that will happen someday.
Have you? Do you have is there an idea for how to do that you've heard of, or for how to achieve that kind of accuracy?
Yes, there are ideas, and I'll mention one. It came out of a project. So I have to tell you my failed project. You're more interested in my successful projects. I have many failed projects, but you should always learn something from your failures. And so I had a very big NSF project to replace the transistor with a new device, a new transistor that is more sensitive. Then we could lower all the voltages in our chips, and they would consume less energy. And in principle, if you did it well enough, you could reduce the energy requirement in chips by 1,000 times, because you could go from a volt to, let's say, 10 millivolts. Did I say 1,000? I meant 10,000 times. Let's say you lower the voltage from 1 volt to 10 millivolts. Well, why does it take 1 volt to switch a transistor? Why can't you switch a transistor with 10 millivolts? Maybe even 1 millivolt. If the transistor was sensitive enough.
Well, there must be a limit from thermal fluctuations or things like that, where if it's extremely sensitive.
Yeah, but the thermal noise, if you've done any experiments, you look on the oscilloscope and the thermal noise is less than 1 millivolt. So if you have 10 millivolts, you have a big safety margin.
Okay.
Now, if you reduce your voltage from 1 volt to 10 millivolts, that's good, 100 times less voltage. But in power, that's voltage squared. Now you've reduced the power requirements by 10,000 times. And that remains a very attractive goal in electronics. We tried to do it, and we ran into this problem of inhomogeneity. So then because let's say you have one device, it would sort of work, but on the other device, it would also work at a different voltage, because not every atom is exactly identical.
And how does it work? You always have to drive at the one that's the highest, or you always have to drive at the highest voltage?
No, you want them all to be identical.
But are they even identical on the today's chips, like standard?
No, of course not. That's what we're trying to replace.
I see.
Okay, so we're trying to replace today's chips with transistors where everyone is atomically identical.
And that would enable, because then is the point that in today's chips, the worst transistor determines the voltage or something like that? They have to drive at 1 volt because some of them have.
Yes, there's a lot of inhomogeneity that way, and they want them all to go. They need all of them to go, and so they just overdrive it with extra voltage. Yeah. And so here we are today, and your cell phone has the chips are running at a volt. Your computer is running at a volt. Everything's running at a volt because the transistor is insensitive. So you asked, how do we make it more sensitive? Well, if everyone was identical, then we would need less voltage. And then you asked how to make it identical. So the way you make it identical is it becomes, in my view, the first rationalization for molecular electronics. And so why don't we make a large molecule which performs the function of the transistor? Now, the transistors are getting to be the size of molecules anyway, so we can do that, and we can make the molecule out of, I shouldn't call them graphene because they look like graphene, but they're actually just polymers that are in the polymers that are strips.
Benzene rings.
Yeah, they're strips of benzene rings and things of that sort, and we could make them identical for the following reason. Let's say you had a prescription from a doctor, and he says, here's this organic molecule in a pill, you're supposed to take it. And you buy it from the pharmacy, and you say, well, how pure is this chemical? Well, its purity is 99.9%. And so now you have identical 99.9%. So why should I take that? They should all be identical. Okay. And so the chemists have ways of purifying things, not pharmaceuticals, but other things. They can purify them beyond 99.9%. They can purify them, for example, 99.9999%. And once you get to 6 nines, that's the purity we need for transistors. And in principle, that can be done. With various types of polymers. But it's a huge material science project. We have so many things to resolve, and it's going to take decades. So ultimately, our electronics will run at much lower voltage as a result of the much greater reproducibility of the transistors. But it's a very daunting material science project.
So maybe to conclude on the strained laser. So what were the practical implications in terms of how much was the threshold current reduced, or what were like the future? What kind of new avenues it opened?
Yeah, to give you a flavor of what it's like in the semiconductor laser field, the first lasers would last for 10 seconds because you had to put so much current in them they would burn out after 10 seconds. And you would be putting 10,000 amps per square centimeter in. And then it got down to 1,000 amps. And then they made ordinary quantum wells, and they got to a few hundred amps, let's say 300 amps per square centimeter. And then they put in strain, and they got to 30 amps per square centimeter. And so this is roughly how that field progressed. But this was like everyone thinks, oh, semiconductor laser, it works. No, it doesn't work. Typically, they die right away. And to have one that works a very long time, you had to bring new scientific knowledge in. So strain was part of that.
Well, did it help, because it's related to this lattice mismatch, maybe like bring new materials, maybe open space for new types of lasers? Because it seemed like before people were fully concentrated on matching the lattices, and they were very restrained to specific types of how much of the open it should be.
Yes, yes, you're absolutely right. It opened up a degree of freedom. And so up until then, they couldn't make red lasers. And so now they put in some indium, and suddenly the infrared laser became a red laser. And so it became the dominant laser. If you have a red laser pointer, that's a strained laser. If you have a DVD player, that's a strained laser. So almost all laser applications in semiconductors are strained now.
Was it patented?
It was patented, but the company was not interested in pursuing the patent because of the way it worked in the Bell system. They had to freely patent because they were a monopoly. They had to freely patent to other people, and so they didn't enforce.
You mean like they had to license patents?
Yes, they were forced by a judge.
That's interesting.
To license patents. It's an interesting industrial history. They found themselves in 1959 with 0 patents because the judge said you have to license all the patents. And after that, they hired vast numbers of scientists. We have no patents. We need more patents. So they hired a great many physicists to create more patents. But all the patents were taken away by a judge at a certain point in time. So they did not pursue the patent.
Okay, lots of questions about the transistor actually. So you were saying that kind of the path where you could see it becoming molecularly accurate, atomically accurate, is basically chemistry.
Yeah.
How do you envision this? Like, is it still on a substrate? Is it some type of 3D system? Like, how do they become an array or a system?
The way you have to think is you have to think that the organic synthesizers, the chemists who do organic synthesis, you have to think of them as gods, and that they can make any structure that you can come up with. And of course, in practice, they have a very difficult task. They need vast numbers of graduate students. It takes a long time, and so on and so forth. But to give you an idea of some of the problems, let's say you have the perfect molecular structure. It has a source, it has a drain, it has a gate. Everything's working fine. But if you lay it on a substrate, everything's disturbed because the substrate disturbs all the energy levels.
Yep.
So now you have to have a way for it to be slightly above the substrate. so to keep the energy
Like
low.
under etch it or something like that.
Under etch it or just do something clever. So you have a whole series of practical difficulties that someday will have to be solved.
Okay, interesting.
But then once you're talking about that, you're talking about pie in the sky R&D that might or might not happen in the future.
Did you consider DNA or another like a biological thing that could be manipulated with grown
Yes,
different
but
ways?
DNA can be manipulated, but other things can be manipulated also.
Yeah.
The chemists can make any polymer they want. Often the polymers are grown from the tip, just like DNA would be grown from the tip. They put a different reagent at the tip, and then they go back to the original chain, and now you have a double heterostructure by chemical growth. And they do that. That's actually quite normal for them. But I want to contrast things like that are pie in the sky versus, for example, the strain laser. It's everywhere. It's adopted. So some of the ideas get adopted. So I've warned you at the beginning that there are going to be many failed ideas. Okay, and like Thomas Edison said, I have to have 1,000 failed ideas, and I have to test them all. And the Edisonian method is you just test one thing after another.
How did you bin the chemical, basically the molecule transistor as a failed idea? Like what?
Okay,
what,
I admit it as a failed idea because we were extremely well supported by NSF for a 10-year period.
Okay.
It was enough time, and then I had to say it may not happen in my lifetime.
Okay.
Okay, and so therefore it falls into the bin of I won't call them unsuccessful ideas, but it's different from an idea that is used. So I have to confess my ambition. Now, this was like a ridiculous ambition that I never really believed that I would ever have this experience, is that not just to invent something that somebody uses, but to invent something that everybody uses every day. Okay, that all of humanity uses, and they touch it, and they're not aware where it came from, but they use it every day. And I'm utterly shocked that I've actually done that 4 times. But there are many times when I had great ambitions, and of course did not work out in that way.
Okay, yeah, that's very interesting.
So let's maybe talk about your other seminal paper related to that period when you were in Bell Labs. So that's photonic crystals.
Yes, I should mention that by then it was split. It was not Bell Labs; it was Bell Communications.
Oh, Bell Communications.
Okay,
be more precise.
And we had a rivalry. Okay, and so we're very proud. We have an alumni association from Bell Communications and so on. But the strained laser is the first thing I did at Bell Communications. So I think probably you want to go to the second thing, which is the photonic crystal.
Yep.
So let me describe how that arose. And it arose in a somewhat...
Which, by the way, I'll just say, like, from my outsider view, I feel like the photonic crystal is the most famous in the optics or, like, academia community. But I think a lot of the other things you've done are more exciting, at least to me. Like, the laser seems to me like a good idea that worked, whereas the photonic crystal, I feel like I keep seeing it in papers and things like that, but I never...
So I'm going to tell you more
about photonic crystals.
Okay, I will answer that question. Yes, that's a very good point. So let me describe a little bit of the history of how I came across this. I was reading Phys Letters, and there was a certain year, I think it was maybe 1985, in Phys Letters, there were 4 papers that said we're going to control spontaneous emission with what we would today call a vertical cavity structure. And these are like today's vertical cavity structures.
Bragg gratings.
They were, I wouldn't call them Bragg gratings, but they were layered structures. They were one-dimensional Bragg reflectors. And I looked at that, and I would read the papers, and there's another one. And don't they realize that the spontaneous emission can escape sideways? But they were claiming that they would, by analogy to metal mirrors, you can actually have a more significant effect on the sideways transmission as well. But these are not metal mirrors. These are Bragg mirrors, one-dimensional dielectric layers. So I said, well, how do we solve this problem? I said, well, we need periodicity in the lateral directions. So I said, well, what kind of periodicity am I going to get in the lateral directions? So I said, I need periodicity laterally. So I I did it like this. And then I said, I need the other direction as well. So I did it like this. And then I looked at this and I said, oh, there's more. These lines are sort of concentrated where they cross. So I made little diamonds here just to indicate that there's more substance right at these vertices. And so I had more substance and I filled it in and did the rest of it. And as I did the rest of it, I came to realize that I had built a checkerboard or a chessboard. Okay. And I looked and I said, oh, a chessboard. Okay, chessboard. That's my starting point. I have my lateral periodicity. It should look like a chessboard. And then I said, what are we going to build up on the chessboard? And wherever we have a black square, here I'll put a white square. So half of these are white squares and half are black squares. And so I said, good. And then I said, I'll go to the next level up. Wherever there's a white square, I'll put a black square on top of it. And on the black squares, I'll put a white square on top of it. And then I realized I had made a face-centered cubic crystal. And I said, well, that's really, that's very interesting. It's a face-centered cubic. So maybe the whole thing, you finally will be able to control the spontaneous emission if you don't make a Bragg structure, make a face-centered cubic structure, okay? And then I, being trained in solid-state physics, I knew what the Brillouin zone looked like, and I knew other Brillouin zones. There are many Brillouin zones that you learn as a student, but the roundest one, I needed a very round Brillouin zone because if it had sharp spikes going out, that would be at a higher frequency, and I needed the forbidden band all to be at one frequency, and so I realized that, maybe the face-centered cubic is the best structure. And when I realized that, I realized I had come up with something non-trivial. It wasn't just drawing pictures on a page of that might end up looking like a chessboard, but that there was a reason for it to be face-centered cubic. And at that point, I realized I had something. And I would say that was a very productive period because that whole exercise took 2 weeks. I got the whole idea in 2 weeks, which is, I myself and others find that to be totally shocking. And so I think that the nature of the photonic crystal originally, the idea was to make the analog of a semiconductor so that in electromagnetic waves you would have a forbidden gap, just like in semiconductors you have a forbidden gap. This is another area where you need to have some background in solid-state physics, so it's going to be a little hard for the medical doctors. But the idea was to have a forbidden gap, and then if the semiconductor would want to emit light, and the semiconductors are fantastic. They absorb light, they emit light, they do everything, but they couldn't do anything in a photonic crystal because there was no light. It was completely forbidden that there should be any electromagnetic waves. So that was a very big deal, and that's I put that into the title of the first paper, Inhibited Spontaneous Emission. Okay. And it evolved. It became a very big field because it was intellectually interesting to extend everything that was known about semiconductors, which is a lot, and it had been overlooked that you should know this also about electromagnetic waves. And if you go back, the one-dimensional version, the Bragg version, was actually first conceived, and the band gap was calculated by Lord Rayleigh in 1887. And so people had known about the band gap in one dimension since 1887, but no one considered how to do this in 3 dimensions. So somehow this has been overlooked. So we went and published it, and there was simultaneously there was an assistant professor at Princeton, Sajid Khan, who had the same concept in mind, but he had a completely different application that had nothing to do with semiconductors. And so we published independently, but within a few weeks of each other. And so we are regarded as the founders of this concept. But the idea went forward, and literally tens of thousands of papers have been published on photonic crystals and photonic band gaps. And you bring up the question, why isn't it commercial like some of my other ideas? And the reason is you could tell right away. The goal was inhibited spontaneous emission. You had no spontaneous emission. You had nothing. And we regarded that as a great achievement to have absolutely nothing. Unfortunately, nothing, you can't sell nothing. Okay. And so to use this in a useful way was not clear that you could use it because it actually prevented an LED from working. If you want to make an LED out of it, it would actually prevent it from being successful. So where did it end up being successful? Is if you remember this two-dimensional picture I drew, it also acts as a diffraction grating for something that came some years later, the silicon photonics. We now make optical circuits in a thin film of silicon. Okay, and one of the biggest issues is how to get the light in and out of the silicon. And one of the easy ways to get light in and out is to make a grating. But one of the problems in making a grating, and it is a general problem in optical communication, is that once you have twisted an optical fiber for optical communication and you twist it around corners, then what happens is you lose track of the polarization. Every time an optical fiber is twisted around a corner, and of course when you install it, you don't keep track of all the corners you twisted around, you end up with your optical information is now in both polarizations. And so you need to have a way to accept both polarizations and to get the maximum amount of information. And so this became a problem in silicon photonics because the initial application was optical communications, is how do we distinguish between the two polarizations? Because if we have a diffraction grating, it's usually just lines, it's parallel lines, it's in one dimension. And so the idea emerged, and it emerged from a Canadian company, but also it emerged from one of the employees. We hired the most brilliant employees we could find, of course, for Luxtera, and came up with the idea that you would have a two-dimensional grating, would be able to separate both polarizations, as just like my fingers, and we would just pattern this into the silicon, pattern a two-dimensional grating into the silicon, and this is how the light goes in and out of silicon photonics. And this is actually how it's done. And each polarization then is separated because one diffraction grating sends the light one way and the other diffraction grating sends the light the other way. And so you have two parallel channels, the same information, but you don't want to waste any light. And so it was extremely well adapted towards silicon photonics. And this ended up in the Luxtera chip. Luxtera ended up being acquired by Cisco, and the main application for these chips was not normal optical communication, but it was slightly shorter distance communication inside the data center. And because it was single mode, we were the only technology that could deal with the size of data centers. Can you believe the data centers can be over 1 kilometer in length?
Wow.
It's mind-boggling. They build them, the big ones they build in the Pacific Northwest, where electricity is supposedly cheaper. And it's a huge building that goes on. And those are your data centers where your emails are kept and your personal private pictures and whatever you have.
So wait, let's dig into that. So it's basically like for optical communication, that's a pretty short distance, like the 10 feet to 1,000 feet type distances.
Right.
Why was the so I guess we didn't really go into the details of Luxtera, but basically it's a transceiver.
A transceiver. I think the question is, why couldn't we compete in long distance communication?
Well, I think the first question is, what's the benefit in that to split the polarization? Basically, is it just a matter of like not losing that light?
Yes, it's basically a matter of not losing the light.
Okay.
And why should you lose it if you don't have to? And it's already difficult enough to compete with other forms of optical communication where everything is made by hand in a very handmade way, and they have very low losses. And you need relatively low losses for long-distance optical communication. But we were not competing at in the realm of the best optical communication. We were competing in the realm that made sense for silicon. It was mass production. So why bother doing it in silicon if it's not mass produced?
Low cost.
So if it's low cost, you need to make a difference. If it's low cost, you need to make millions of them.
Yep,
Okay,
yep.
and a chip is a failure if you only make a million of them. Okay, so that's part of the creativity of a designer in electrical engineering. It meant he designed an unimportant chip. What, you made only a million of those? So, so we were in that realm. We had the mindset that we would take advantage of we're doing it in silicon, is we can make millions at low cost, and so we needed to go to a broader market where they were not handmade. We could tolerate a little bit higher insertion losses, and part of the insertion loss was the grating coupler, and it was an automatic way of getting light in and out, but you lost some photons doing that. So anyway, they perfected it, and the insertion loss was low enough, and it became the standard way of doing optical communication at data centers over that range of distances. And so what I like to tell people is that if you checked your email today, you probably used a photonic crystal, because the two-dimensional grating coupler is essentially a two-dimensional photonic crystal.
So,
and it has many of the attributes, has the high index contrast because it's silicon versus silicon dioxide, etc. That turned out to be the biggest application for photonic crystals, and it falls into this category that I told you about. It's something that everybody in the world uses every day if you check your email.
That's awesome.
So then it seems like with photonic crystals, I can see that they are widely adopted by nature, by butterflies, peacocks, and all the other types of fancy animals and insects.
Yeah.
In semiconductors, you said it's for the polarized beam splitters. I can see definitely a lot in academia. It's used for quantum photonics, the photonic crystal nanobeams cavities.
Yeah.
People really like them. Maybe if you can overall give a big picture of what are currently the main trends of photonic crystals, where they have been used, maybe photonic crystal fibers. That's what I have heard. But how is it related to the concept of what you have introduced?
Yeah. So it's a lot of it falls into the same category as Edison with his 1,000 failures in order to achieve one success. So but your statement was very accurate about the idea that we're all very surprised that nature has so many photonic crystals, and even the diamond structure photonic crystal occurs on certain beetles. And in hindsight, it's, oh my God, it's all over the animal world and so on, but not so much in technology. And the technological applications tend to be very scientific, as you mentioned, quantum devices and so forth. So I try to give a counterexample. Yes, well, we use it in data centers, the internal communication in data centers. But I think your description was quite accurate. The most surprising aspect is that it was physics, but somehow we discovered a part of the animal world that we had not been aware of.
Do we humans also have any photonic crystals?
I'm not aware. I'm not aware that humans have photonic crystals as part of them.
I mean, I think the fact that photonic crystals exist so much in nature and not yet a lot in human engineering systems is probably just reflects how cheap nanoscale fabrication is for nature, because it's all ground up. They can just use it as paint, right? So we have to actually use physical paint to paint. We can't nanostructure the walls of our buildings, right? If we could, they would be whatever color. You can get whatever color you want.
The animals, for example, parrot feathers. They've two-dimensional photonic crystals. I mean,
exactly.
Many of the things that
those would be like $20 a piece if you had to fabricate them, or maybe 50 or something.
Well, I'll give you an example, very influential, but I think maybe, Michael, you might remember this, is that the symbol of the RCA television network was the peacock. Do you remember this?
I don't think
it was the best logo you could ever have, because
yes, okay, I do remember.
part of RPA,
Yes.
it was a logo, and it was the purpose of the logo was to tell you we are the developers of color television. Created color television.
Right.
And so it was an extremely successful logo. And I kind of grew up on that. And they stylized it and they changed it and modernized it over the years. But it was still the peacock feathers. And so it came as a big shock that the color of the peacock feathers is coming completely from photonic crystals. And so that's sort of an example that the photonic crystals ended up being more important in the animal world rather than in the technology world. But the reason is clear. The reason is that the idea was inhibited spontaneous emission. You suppress light. Nobody wants to pay you for nothing for suppressing light. So the applications are there, but they're maybe they sound a little prosaic or specialized.
Do you get emails like every time somebody makes a strange photonic crystal or a new paper? Do people forward them to you? Look, another photonic crystal.
I think people are very reasonable. They only forward it to me if it's really a surprising new insight, which I did get some time ago from the basically diamond structure photonic crystal. Who would think that nature could figure out a diamond structure photonic crystal? Well, nature figured out diamonds, so they figured out how to make colored beetles.
So is it fair to say that photonic crystals are mostly used to attracting the opposite gender?
Yes, and in fact, in part, they're used for makeup. So even for people, that they're one of the ways that they produce dyes for makeup, and they're physical dyes. So
I guess one thing that we were curious about. So after your time at Bell Labs, you kind of decided to go back to academia. So this was after having published these two really interesting results. I guess the strained laser result people got excited about after the photonic crystal, or like which one was the one that got attention
I would
first?
say that that's a little hard. Depends on how much attention. But one was more an academic thing where people would write a lot of papers.
Mm-hmm.
So the first 5 years, there were very few papers on photonic crystal.
Oh, okay.
And then it grew to be a gigantic number of papers. So it took a while for the idea to catch on. Whereas the not the quantum well, but rather the strained laser, that was sort of a step function. It was a technological. It was a drop-in technology, so that you don't normally you just change one thing and it gets adopted. And because the rest of it is already ready for it. So people are already making semiconductors, they know how to package them, they know how to use them, they had customers, they had applications. You drop in one little change and it gets adopted all at once. So it's the two things are somewhat different in that respect.
And when you decided, what was kind of the transition when you decided to leave Bell and go back?
So then once again, I would say it was involuntary once again.
Okay.
In the sense that the Bell Communications was being supported by the Bell operating companies, which is the local telephone companies. I thought they were more reliable than long distance. I could already see long distance might go away. And of course, nobody saw the future that well. And they decided one day that every time we would invent something, it would help the cable TV companies compete with them. So they said, we're discontinuing research. And so that's how it is in industry. It's they instructed me. I had a large group, and they instructed me, helped them all find jobs. So then I went to my manager and I said, I helped them all find jobs. Now please fire me so that I can get the severance package too. Okay. And he said, oh, no, we want you. We don't want you to leave. We're not giving you the severance package. So
that's very.
So the result of that was I just stayed there.
So basically, a big source of your creativity is just fluctuations in corporate structure. So
yes, you could say that. You can say that. Actually, I think there's some truth in that, because you go to a new place, you meet new people. I'll just give an example. I was at Exxon working on solar cells, but everyone else was in the petroleum industry.
Mm-hmm.
And I learned a tremendous amount about chemical engineering from those people, and things that physicists don't know about. And it was like I was there for 5 years, so like getting a second PhD in chemical engineering because I spoke with them and I learned from them. And so each new job, and just to give another example, when I was a Bell Labs guy, but I was working at Exxon, and Exxon had the refugees from RCA. And RCA was the equivalent company. It was a very highly respected company, created black and white television, color television, created radio, created commercial networks, and so on and so forth. And it was regarded as the equal of Bell Labs in its time, but it's a different group of people. And you think, well, they're both doing industrial research in electronics, and they thought very differently because they were both a little bit ingrown. They were both so successful. They were ingrown. And to get both viewpoints, I regard that as a great privilege. And that's part of why I enjoyed my relationship with Al Rose. He was total RCA guy, and he thought about things extremely differently. Sort of a different way of doing solid state without the transistors. And so it was much more general that way. So I saw both sides by going from company to company, but in some cases, the transition was rather involuntary.
I would say like your professional path is very distinct from the traditional, let's say, getting a PhD.
Yeah, but it's like
assistant professor.
Yeah, but it's
in the tenure.
What you're describing is not traditional. Actually, what you're describing is the current situation, and it's part of the pressure we put on young people is that they have to stick to academia, and if they deviate from it, they're out. Okay, and didn't used to be like that. I jumped back and forth several times, and was perfectly respectable. Of course, I was tending to go toward electrical engineering rather than physics. But it didn't matter. I had lots of job offers in physics departments too. In those days, you could jump back and forth, and I think it's extremely unfortunate and a disservice to the young people that we force them. So the traditional situation is you had freedom, and now you have less freedom because you have to stick to one path or you're in trouble.
You have also better understanding of what is happening in the industry, of how problems are approached.
Exactly.
Because I feel like there is a big detachment between understanding like academia world and
I pity the younger professors in that they don't have the general knowledge of different fields, and they're deprived. They're forced into a narrow specialty. This is very unfortunate. And so I count myself very lucky that I was jumping around and learning about different things. And also there's a great truth. In one field, you might run out of ideas. You got to jump to another field where there might be new ideas. And the way I did that I always looked for something that I could see, this seems to be not well understood. Okay, probably something could be done.
Period is about 5 years, it seems.
Yeah, but you could have some things that are not understood for 100 years, like this.
No. I mean, just in your path.
In my path,
out of 5-year chunks, which is funny because
it came out. Some of them are 2-year chunks. Some of them were 7-year chunks, etc. But
yeah, well, how much time does it take? So you've gotten into a lot of new areas, right? How much time does it take before you feel like you're really, swimming comfortably in the information, kind of like in the space? Like how
it's pretty much right away, because right away you can see there's a mistake. There's something fishy.
That's what gets you interested in.
And I'll just give an example because we're supposed to transition to the antennas at some point. So when I was at UCLA, we had a great reputation as being the university to go to for electromagnetics.
Mm-hmm.
And then what was the biggest thing happening in society in the 1990s? Everybody was getting a cell phone. Okay, which when I was at Bell Labs, that was regarded as impossible. How could you have cell phones? Then we wouldn't need a monopoly, and then there would be no Bell Labs. Okay, they didn't realize. Yes, that's right, and it's going to happen. Okay, so I went to my colleagues, and at that time, what was very popular, the really small cell phones were very popular, and very sexy.
Which year was that?
It was let's say 1997 to 99.
Is it the Nokia? The small one from the Motorola's?
At that time, the Motorola flip phone had taken the world by storm, and you could prove that you were cool. And it's a lot smaller than today's flip phones. It was a tiny phone. And then So I went to my colleagues and I asked them, how could you possibly make an antenna for these very tiny phones?
Smaller than this one?
It was about that size, yes. How could you make an antenna for a phone that was so small when the electromagnetic wavelength is much larger than the size of the phone? And then I went to other universities that were very strong in electromagnetics, and I asked them, can you explain to me how the cell phone antenna could possibly be working? And after I have done that a few times and a few experts, no one could really explain it to me. And so I decided that maybe that could represent a business opportunity because it didn't reach my level of satisfaction of there being a good explanation how it works. And so I'll share with you something I do in my class. So I was teaching the senior electromagnetics class. And the first lecture, I come in and I show them, this is what a cell phone was in 1990. And here it is in 1993. It's completely different. And here it is in 1996. They changed it completely. And here it is in 1999. Again, it's completely different. And in 2000, it's inside it looks different because it's inside the phone.
Was it some kind of Edison approach?
No, it was it was trial and error, but it was unsuccessful trial and error. It was what Edison promised, is most of the trials would not work. And in effect, when they brought out a new phone, and this was not like an experiment in the lab, they were producing hundreds of millions of phones. And then 3 years later, they said, no, we designed it completely wrong. We have to change the design. And then the new design is also completely wrong. And they changed it again 3 years later. So you could tell there was a problem. Why do they have to keep it? You think they would focus in on the right design and they would do it right, and they would do it that way indefinitely.
And what's the main problem with antennas? It's in some places you can get the signal
well,
quality.
Okay,
Bad.
let me explain what the main problem is. And I have one of my papers shows it. There's something very important to know about antennas that is not well known to, not known at all really to physicists, and even to electrical engineers. It's hardly known. And it's something called the Wheeler limit. So let me explain who Wheeler was. It's not John Wheeler, who was Feynman's thesis advisor. It's another Wheeler, also of very high accomplishments. No relation as far as I know. And his name is Harold Wheeler. And Harold Wheeler was born in 1901, and he was in college at George Washington University in Washington. He was a college man, and he, like in the early days of computers, only teenagers would understand computers because parents could not possibly understand it. But that, if you're looking at the period at the end of World War I, the hot thing was radio, and he understood. He was a teenager who understood radio, and he was a student at George Washington University. And then he was hired by what we call today NIST as a summer job in a physics lab. And his function in it was to explain radio to the older scientists that were working there. And he was just a teenager, a summer student, and he would explain radio to them. So he became a very important radio engineer afterward, and but he did not have a PhD. So then World War II breaks out, and they bring all the smartest people together at MIT in the MIT Radiation Lab. But the price of admission, you had to have a PhD. And he did not have a PhD. So but the government wanted him anyway. So there was a U.S. Army lab, today called the Harry Diamond Lab, that invented something very important in World War II called the proximity fuse. And the proximity fuse was a very primitive form of radar. And the proximity fuse is you would shoot an artillery shell at an airplane. You didn't have to hit the airplane. You had a little radio oscillator. And if the frequency of the oscillator would shift slightly by the presence of metal, the frequency shift would be picked up and the munition would explode. Okay, so that was a very important invention in World War II. So he was responsible for that, and it had many different aspects. It was not invented at the MIT Radiation Lab. Of course, at MIT, they think they invented everything. Isn't that right? Yeah, he's nodding. Yeah.
Partially.
Yes, okay.
Radars, AI,
Okay, but this was a primitive form of radar that they didn't invent because the little radio oscillator was sensing the metal of the target. Okay, so yes, MIT takes credit for a lot of things that were done in other places. That happens a lot. That was true at Bell Labs too. So this is Harold Wheeler, and then the war ends, and he learned something while designing the proximity fuse, and he learned something since it was a primitive form of radar. And at that time they could not generate really high frequencies, so the electromagnetic wavelength was much longer than the artillery shell. And so, how do you make an efficient antenna if you don't have adequate length? The proper antenna should be at least half a wavelength long. So it was a war secret. Then the war ends, and he publishes a paper, and I wonder if you can focus in.
So just to be clear, this shell has a radio transmitter and a receiver. And so basically, as it's passing the airplane, the reflections get received by the antenna.
Yes. And the transmitter was the receiver, both.
It's okay.
Okay.
Got it.
And the antenna was act both as a transmitter and a receiver, both.
Got it.
Okay. And so it was sensing the environment. It was sensing the environment by radio.
Yeah.
Well, we have a word for that. It's called radar.
Right.
Okay. And I don't know if whether it was in the near field radar or far field radar, but so he comes up with the idea, and this is an idea that I used to tease my students when they would come to the first class. I would show them all the old cell phones, and hundreds of millions of units were produced, and 3 years later they would decide it was the wrong design, and then I would ask them, like I asked you, what is your personal resonant frequency? And since you're both about 2 meters tall, I know your personal resonance frequency is 75 megahertz. Okay, and some of them guessed it. Some of the students would guess it. Then I would say, well, not to get too personal, but what is your personal Q? And of course
imaginary Q.
We don't do imaginary.
Well, IQ.
IQ. No. No, it was electromagnetic Q. Okay, and so Harold Wheeler tells you for every antenna there is the lowest Q you can achieve. So I have to explain something about antennas. In antennas, in the rest of physics, you always want the highest Q possible. But in antennas, you want the lowest Q possible. Why? Because you want a wide bandwidth so that you can accept, let's say, phone calls. You don't know who's calling you, could come at different frequencies. So you need a very wide Q, a very wide bandwidth. A wide bandwidth means you have a low Q. So this is completely counterintuitive to every physicist, there is a tremendous prize waiting for you if you can get low Q. Okay. And so in cell phones, you want the lowest Q possible. The bandwidth that is used between the European band and the American band, it's over 100 megahertz, centered around 900 megahertz. And so you need a Q. You'd like to have a Q of 10. Even lower would be nice. So let's say Q of 10 would be good. And it's actually, most of the time, if you just make an antenna, your Q could be much larger, particularly the small ones. So the small ones have a very high Q. So he tells you, and this is the formula that you should pick up on your video, is what is the Q to expect depending upon the size of an object. And the A is the size of the object, lambda is the electromagnetic wavelength, and Q is the frequency over the bandwidth. And I suppose I should add that to the equation. So you want the lowest Q, you want the widest bandwidth, and the lowest Q. And it seems like the people who were designing the cell phones were not aware that they were up against the Wheeler limit. And so they were designing the antennas completely wrong, even though they had access to the best consultants in the world. And that's one of the reasons I say the people who really understood antennas were the World War II radio engineers, because then it really mattered, and radio was very important in War II.
And maybe you can give it, what's the intuition behind the Wheeler limit? Like, why is that? Like, what's the intuition?
Okay, that's a very good question. Let's say you're trying to make a dipole, and then you switch the dipole at the frequency, the radio frequency. Then if you have the positive and negative charge are very close together, you make a small dipole. So it doesn't radiate very well. Okay. And if you pull the positive and negative charge apart, you have a much bigger dipole. And so if the size available is very small, like on a very small cell phone, as they used the style was to make them very small, if it was very small, you could not get a very, very big dipole, and you simply wouldn't radiate as much. And if you don't radiate as much, we're really talking about radiation Q. The losses, hopefully the losses would come from radiating electromagnetic waves and not from simple resistance. And so there's an inherent disadvantage. And this is the formula he derives. It's actually, I wrote it as an equality. It's actually an inequality, because you work very hard. You can't quite get the lowest Q possible. So this is an inequality. Now, maybe you've learned in different books, like maybe, did you learn from Jackson?
Yes, when I was at Purdue, I learned from Jackson.
It's very, very unfortunate, because it doesn't really explain antennas in Jackson. Even though this formula, at the time Jackson wrote his first edition, this paper had been published, but this is published in the engineering literature, not published in the physics literature. And Jackson was probably of the opinion that everything important in electromagnetics had been done at MIT.
Yeah, I learned about antennas actually by trial and error during my PhD.
Okay.
Instead of from textbooks.
Okay. Well,
but there was different types of antenna.
Yeah, it depends upon the kind. Yeah. So even for those, you could benefit a lot from what Harold Wheeler said. So those guys who were the World War II radio engineers, by the time cell phones came around, those guys had all passed away. Okay, and there was nobody around to tell them how to make a proper antenna for a cell phone. I'm totally convinced if those guys were alive, the problem would not have existed, because they had already invented many other things. Just to give you an example of something else they invented, which is much more complicated than the cell phone, is the AM radio antenna. And the radio wave, the AM radio is 300-meter wavelength, and the radio antenna is 1 meter long. That's ridiculous. How does it work? Well, it's even more clever than the cell phone. I won't get into it. But those guys figured that out with the knowledge that was available in World War II. So people had AM radios in their cars starting right after World War II. They had figured this whole thing out. So here we were. It was a big industry, cell phones. Everybody was getting a cell phone. I got a cell phone. How does the antenna work? So I was convinced after speaking with the experts that I could not get a good explanation. For me, as you know, that I mentioned, that's good enough. Let's start a company then and figure it out. So at that time, it was very easy to raise money, because it was during the internet bubble, and you could practically just walk into a venture capitalist, and they would ask how much you wanted. And so they wanted things in optics. I said, no, there are too many optics companies, radio. So they said, okay. And all I had was knowledge that the way other people were doing it was incorrect. But about 3 months after starting the company and working a little bit, I said, oh my God, I know nothing about antennas. And I am in no position to start a company in this field. And I went back to the investors. I said, I'm sorry. I don't really, I had a patent. The patent is really not any good. And would you like your money back? And the way it was at that time, maybe even today, they said, well, you have a team. You're smart guys. You'll figure this out. we can't give you your money back. And later I found the real reason. They have so many investors, it would be extraordinarily complicated to give the money back. It's like you have a grant from the government, and the funding agency will hate you if you try to give the money back because it creates so much paperwork.
What was this the first startup that you had been?
Yeah, that was the first startup.
First.
And these were very reasonable, generous people.
Do you think that if not for the tech bubble, you would have just done it in academia, like more like just publishing something? If there wasn't this very easy path to starting a startup at the time, would you have done
I
that?
wouldn't have done it at all because I was in over my head.
Yeah.
And I knew I was in over my head. I did not understand antennas, I realized.
Oh, but I just mean even starting, like going and raising money or hiring people, whatever it was, like would you have done that if it wasn't like the height of the bubble?
Well, that played a big role. So, for example, I had a colleague, associate professor Henry Samueli, and Henry was just founding Broadcom, which is a huge company today, and he was the founder. It was very successful. He managed to do it. He did it the right way. He raised very little company after his first. That was the second company. His first company, he took money from venture capitalists, and then you get diluted. Second company, he didn't get diluted, and he and his graduate student ended up becoming on the Fortune 400 list. Yes, it was in the air. You didn't want to be the last professor who did not have a company. Okay, it was like that.
What was the secret behind Broadcom? Like what?
It was a very, very simple secret. These were the best chip designers in the world, and they had designed their product was going to be a set-top box for cable TV, and then you're too young to remember this, but in the year 1994, everybody adopted the internet. It just happened all at once. It's like a phase transition. And they said, well, I can get internet at work, but I can't get internet at home. So what he had done is he had gone to the Standards Association meetings and he said, we're going to provide cable TV digitally. So you'll have digital television. That was the way it was being done then. And then he realized his digital chips that were meant for television could be easily adapted for the internet. And the chips were ready to go. And he had a 2-year head start over his competitors. And with a 2-year head start, the company became insanely successful because nobody else could deliver product, and he could deliver the chips.
Oh, that's very interesting.
So it's an interesting story. Not too easy to duplicate, and it's in a physics-oriented field. It's a lot harder to duplicate, but there were many other success stories, and for example, many of Henry's graduate students went on to become also extremely wealthy, and there were companies being started all over the place. So I said, I don't want to get left out, and it was relatively easy to do. And I said, this is going to be my niche. I'm going to solve the cell phone antenna problem. Except that I realized that I had no idea how to do it. And a lot of the ideas I had before didn't work out. So I read a great many books, and gradually I developed an intuitive understanding of what was wrong with cell phones. But even then, it wasn't clear. But I came up with a very good idea for the people inside the company. I told them, in electromagnetics, you have something called a network analyzer that has...
I just have a question before you go into that.
Yeah.
So when you started the company, you were on the board and still at the university, right?
Yes.
How did you recruit good people to do this? Like often the first startup is just practice. Like it's rare that the first one does well. So what was your process?
It's like a lot of other professors. First of all, we're highly restricted at the University of California. We cannot mix our commercial work with the work at the university. It has to be completely different research. Yes, it's very severe restrictions. But what happens? Let's say you have a postdoc, and the postdoc wants to go somewhere, and it's a very good postdoc, and say, well, academia is okay, but you can make a lot more money if you go to a startup. So you persuade them to go to the startup. And once you have one of those people...
That sounds like me.
Yes, that's right. And once they say, well, I know someone really good back in France who is quite authoritative in electromagnetics, so bring him in. Oh, he wants to be the CTO. Okay, we need a CTO. He has a work experience. He can be a CTO. And it was like that, and it was very easy to do. I just sat on the board of directors, and they did all the work. But I would consult with them, and I would give them ideas. And I gave them an idea, which is an extremely trivial idea for people who are sort of vested in the business. So in electronics, we have something called a voltmeter. And then you can imagine something called an AC voltmeter. But if you have if you do really important detailed work, AC voltmeter is nothing. You want to have a full network analyzer, which basically is like an AC voltmeter with all the bells and whistles, measures all the phase shifts, etc. And so I said, well, you can just use that as a radar machine, because it has an output, it has an input. The output could be like a little transmitter, and let's say you have a cell phone. You don't have to touch it even. You just be near, could even be half a meter away. The little antenna that you put at the transmitter terminal is going to sense the presence of the cell phone. And it's going to sense the presence of the cell phone because every antenna is also an LC circuit. Every human being is an LC circuit. I asked you what your resonant frequency was. So they can sense the cell phone. They can sense what the antenna on the cell phone is doing, even from half a meter away. It's kind of radar. And then you sense it back. The signal goes back into the network analyzer, and you're sensing the LC circuit in the cell phone, and you're sensing the bandwidth. So it would take you 30 seconds to see if you made a successful antenna, if you made a successful design. And so they did that, and one of them in particular listened to me, and he started doing this. And he went with all, and it takes you 30 seconds. You could change the design, twist some metal around, and you change the design. And he started doing that, and he saw the bandwidth became wider and wider when he separated the antenna part from the ground plane of the cell phone. Okay. And for that, I have kind of an explanation similar to the explanation I gave you a minute ago. And the explanation is, to radiate, you have to separate the positive and negative charges as much as possible to make a big dipole. And then it oscillates back and forth with every cycle. That's perfect. And you radiate radio waves.
Like capacitance?
Not like capacitance. Think of a wire with positive charge at one end and negative charge at the other end. So then you say, oh, that's some type of separation of positive and negative. And, well, why don't I put a capacitor? I have positive and negative. I also have some separation. Well, you don't have very much separation because they're practically next to each other. You have an extremely thin membrane that separates the positive and negative, and you have a very small dipole, which is totally useless. Okay, so what happened is they separated the antenna from the ground plane, and the more they separated it, the better the bandwidth was. It radiated better. It was following the principle put forward by Wheeler, Harold Wheeler, not John Wheeler. Okay, and yes, if you have something that's a very small separation of positive and negative, no, that's not going to radiate very well, and so you have to have big separation.
So you mentioned that you had this interesting approach that you suggested to them to characterize the antennas.
That's like an experimentalist thing.
Yeah. And this actually parallels what you were saying about the solar cells, that like once you find a way to characterize the material quickly, you can iterate the material
much faster.
You mentioned checking the illumination.
Yeah, and that was basically that led us to the efficiency record in 2011.
Yeah. And so
but at that time, that what I understood at that time, I didn't realize how important luminescence was, and so the industry went forward just using the light trapping, and the industry has not yet caught up to where they're using the idea that a great solar cell has to be a great LED.
There's still room there.
There's room there, okay? And so, but this was, again, the same thing, maybe a lazy experimentalist. I'm a lazy experimentalist. I don't like to do hard experiments. I like to do easy experiments.
How fast you can improve it, tweaking it.
Yeah, or the Edisonian method. No one respects it. But if you have a very rapid diagnostic, you can try hundreds of things one after the other.
What was the previous way of characterizing this?
You'd be shocked. You'd be shocked. The previous way of characterizing this is you complete the cell phone, and then you send it out for field trials.
Oh, wow.
And they would drive the cell phone around for 2 weeks in field trials, and then come back and tell you how good it was. Okay, and that's what. Okay, so it was. It enabled the discovery of something terribly obvious in hindsight. Separate the positive and negative electric charge as much as possible. Okay, now what were they doing in the existing cell phones? The Nokia phones, the other phones. Well, Nokia was a very successful company at that time in handsets. And you open up their handset, and there was a lot of stray capacitance, totally unnecessary capacitance. Well, what's the problem with capacitance? It doesn't radiate. The problem with capacitance is that the positive and negative charge is very close together. It doesn't radiate, okay, but it stores energy. A capacitor stores energy. So what is the alternate definition of Q? The alternate definition of Q is stored energy divided by lost energy per cycle. Okay, and that's the alternative definition of Q. So you want to store as little energy as possible. Is any capacitance is useless capacitance; it won't radiate, and so you want to cut down your stray capacitance. It's only going to make your Q higher, and you're trying to make your Q lower. And so you open it up, and the antenna was right close to, it's just stupid in hindsight, right? The antenna was close to the ground plane, huge amount of useless capacitance. And just about every other antenna had this problem. Lots of useless capacitance. And then we said, no, you don't want that. You want no stray capacitance at all. Then it performs well. And basically, we figured out that idea in 2004. And the company had been very unsuccessful. So you can imagine the venture capitalists, they were so patient. After 4 years after the company started, we had very little revenue. We had only like $1.5 million of revenue, which in business is nothing. It's nothing. It pays the secretary and the rent. You can't do anything with it. Okay, and they were losing a patience, but they hadn't lost patience yet. But they were getting a little worried. Okay, and then in 2005, we started supplying this to customers, and we had $5 million in revenue. In 2006, we had $15 million in revenue, and in 2007, we had $25 million in revenue, and this is all based on a better understanding of the physics. That's sort of the point that I'm trying to get across with each of these examples, is that it comes from understanding the physics better. And so what they were offering the customers was 2 decibels of higher performance. But in telecommunication, 2 decibels is actually a lot. Okay. And what it meant to the customers were the engineers designing the cell phones. It's very tricky to design cell phone antennas, because you start the design, you have no idea where you're going to end up, because it's like some kind of optimization problem. And because we started with a 2 decibel advantage, we almost always ended up with something that met the requirements. So the engineers only wanted to work with us. And then what happened, the company went on, and Samsung became a big customer. We got our numbers very high. And Samsung in 2012 released the Galaxy S3, the first really good smartphone. They released it, and the engineers said, well, the only company we want to design the antennas, Ethertronics, because when they do it, it works every time, and we get no delays. It works every time. And so they did something they were not supposed to do. They gave my company the worldwide order for all the Galaxy S3s in the world, and it was during the Olympics. It was 2012 Olympics, and you couldn't watch it for 15 minutes without seeing a Galaxy S3 commercial. So what happened that year? Our revenue jumped to $100 million because we were supplying the entire world with the Galaxy S3, and the purchasing department was extremely mad because they weren't supposed to do that. But the engineers wanted us, so we became the dominant supplier to Samsung. And
in parallel, Apple must have been developing their own antennas, or they had a different supplier?
No. In parallel, the Apple invented the iPhone 4, which was a total disaster, a very famous antenna disaster. And my company offered to help Apple. And they said, no. The antenna influences the appearance of the phone because Steve Jobs had an idea, is that the exterior surface of the phone should be metallic and it should be the antenna and would look nice, okay? And it was similar to my pitch to the venture capitalists, is that the antenna will never be commoditized because it will become part of the appearance of the phone. And every company is going to want its own appearance, so it'll never be a commodity, and we'll always be able to make money. But you can read Steve Jobs' biography about the disaster of the iPhone 4, the antenna gate, and they would not take any help from my company because it influences the appearance of the iPhone. And I once sent a student to be a intern at Apple, and I asked him if he had a good time there. He had some reservations. I said, well, did they at least respect you? And he said, no, I had the second highest respect in the company. I said, who had the highest? And the highest were the industrial designers, the artists who designed the cell phone. And the reason he was second highest is he got to talk to them. Okay? And they were the gods of the iPhone, were the industrial designers who basically the artists who designed the appearance of the cell phone. Of course, this cost them. And then they went on for many years, and we never were able to sell them anything, but we knew the antennas we were selling to Samsung were superior by at least 2 decibels to the antennas that Apple had.
So what is the solution? I remember they used the backpad.
It was it was just to the isolation solved the immediate problem. Samsung never had the idea that the exterior skin should be metallic, and they always had a thin plastic layer representing the exterior skin of the cell phone, so they never had that problem. But in any case, we were providing them with a better and more efficient antenna. So this went on for several more years. And then finally, in 2014, I looked at the iPhone 6, and I had originally predicted that other companies would copy, our customers would copy our antenna. But it looked the same as everybody else's antenna. It was very subtle to see what the difference was. And I was wrong. It took 9 years. I thought our position would last for 2 years. It lasted for 9 years.
So the difference was that the ground of the phone, like basically the metal plane of the phone, the distance between that and
the radiating element.
I see.
You try to make it as large as possible.
And how do you do that? Just through the thickness of the phone? It's on the opposite side of the phone?
No, you just leave some space.
Okay.
You leave a little bit of space. Nobody was leaving. No, that's why it was very hard to see. What's their trick? What's their trick? There must be.
Was anything ever published about this?
No, because it was a commercial secret. I'm still planning to publish it, and I don't think it's a secret anymore. The patents have run out. But then I looked at the iPhone 6, which was released in 2014, and our products through Samsung were being released in 2005. And I looked at the phone and I said, they got it. Okay, And if you can visualize what the iPhone 6 was like, the antennas were at the ends. The Steve Jobs insisted the whole skin should be metallic, and the antennas was part of the skin, so it was at the ends. And then there was something a little odd, though, is that the ends were separated from the rest of the metallic phone by 2 millimeters of plastic.
Hmm.
I said, why do you need 2 millimeters of insulation? Okay, what's the voltage on the antenna? Oh, it's like 1 volt. If you have 1 volt, you don't need 2 millimeters of insulation. Okay, and so at that instant, I realized they figured it out. And they figured it out because you didn't need the space. There was no reason to have the space except that it made the antenna more efficient and better and have many other desirable properties. So they finally solved the problem of the iPhone 4. They solved it in the iPhone 6. And at that point, they didn't need anyone to help them. They had figured it out themselves because they have a very good antenna team now. I think they had a good antenna team then, but if you read the Steve Jobs biography, he would always force his engineers to do the impossible. He thought he could make them defy the laws of physics, and he was very hard to deal with, and he was, after all, running the company. So they ended up making a mistake. But I don't blame the engineers. I think the engineers were short-circuited, cut out of that decision.
Yeah, very interesting story.
Yeah.
Yeah, I think we can maybe proceed further in terms of asking some of our traditional questions. So that was about your past experience and your past projects. So, for example, if these days you would be given unlimited resources in terms of financial resources or human resources, what kind of project would you pursue these days?
Okay, that's a very good question. But let me add one more thing about the antenna. Samsung sells a great many. We ended up selling 2 billion antennas, and Samsung was our biggest customer. But the other companies are doing it now. The iPhone does it, and so on and so forth. So I think this falls again into the category of something that because everybody in the world has a cell phone.
Everybody got to the same page.
Everybody in the world has a cell phone. Yes, they're using something that I contributed to that ended up, they most likely use their phone every day. So I fulfilled one of my ambitions. Now, to get back to your questions, if I had unlimited resources, what I would do, I don't live in a world of unlimited resources. It never even crosses my mind to consider unlimited resources. I consider always a balance, that resources are unlimited. Therefore, we have to make things better. Okay, what is the purpose of science? If we had unlimited resources, we wouldn't need science even, right? Because we could fulfill every need we could fulfill with our unlimited resources. So certainly everything that I do, I have been influenced by. Resources are limited. It has to be better than what exists today, et cetera, et cetera. So it's the way I think is that it's our obligation as scientists and as technologists to always make things better because we're always struggling against unlimited resources. So let me rephrase your question. And that is, if you had a lot of resources and you're looking for the most promising area of research, what would you do? So first of all, if it required vast resources, I probably wouldn't do it. Okay, but let's say if it required reasonable resources, what's worth doing? So one of the things I think is very well worth doing now is a field that is emerging but is not yet fully acknowledged. One of the fields that is fully acknowledged is quantum computing. You see quantum computing everywhere. It has its difficulties. But one thing that has been overlooked is that physics itself, without getting into quantum mechanics, already provides a tremendous opportunity for computing. Much computing today involves optimization. So, for example, artificial intelligence is an optimization problem. Designing electromagnetic structures is an optimization problem. Now, how can physics help you solve optimization problems in the following way. Physics has many famous equations, like Schrodinger's equation, etc. But there's another way to express the laws of physics, and to express it as inequalities. And so we have the principle of least action. The Feynman lectures likes to express all physics ideas are in the principle of least action, and from that you can get Schrodinger's equation, but you can get a lot more. There are other physics principles too. There's the principle that a system wants to go to the lowest energy level. So it's an inequality. It's always going in one direction. Okay. There are a number of other principles. Let me mention the one that turns out to be the most useful, but the least respected, and that's the Onsager principle. So Onsager was a very famous theoretical physicist. In 1931, he published the idea. We know about thermodynamics and so forth. Things go to the lowest energy level. Equivalently, they go to the highest entropy. Onsager did something different. What if you have a system that can never achieve its thermal equilibrium because it's constantly being driven? It has a power supply attached to it. Well, that's every circuit in the world, practically. And what laws does it follow? So he says, well, instead of going to the maximum entropy, he says it goes to the maximum, or not the minimum, I should say, time derivative of entropy. What is the time derivative of entropy? Is heat. Time derivative is the amount of heat you dissipate, is the time derivative of entropy. And in effect, what he said is that a driven system, out of equilibrium, it's constantly being driven, it tries to generate as little heat as possible. So let's say the machine is a circuit. The circuit tries to organize itself, so it dissipates as little heat in the resistors as possible.
As little as
possible. Now, I see that you're looking at me like this is weird.
Well, why not as much as possible? I gotta have an intuition why it's not.
No. You have to read Onsager's paper then from 1931, and it is a little bit intuitive, because if it was equilibrium, it would be as much entropy as possible, but this is a different physical situation. So and this is not taught, because I can sort of tell by your reactions that you're hearing about this for the first time.
Yeah.
And it's not taught, I think, as a travesty. But Onsager ended up being very highly respected. And when I was a graduate student, he won the Nobel Prize for essentially creating the thermodynamics of disequilibrium systems. And he said, how do you do it? You do it with an inequality just like other inequalities, like in thermodynamics. And his inequality, the simplest expression, is you minimize the heat generation. And
sorry, I just have a question. So in a simple world where you have a resistor, right?
Yeah.
All the energy you're putting into it is heat dissipation.
Yes.
So does that mean that the resistance increases? Because then you have less heat dissipation.
No, imagine you have a circuit where the wires go in various directions, a little bit like the circuits around this table. It wires everywhere. And then the current can take one wire, or can take another wire,
right,
or can take a third wire, and it will it'll organize itself in such a way that it will end up dissipating the least amount of heat. Now, you can say the current can't just go into any wire, okay? And, it's not quite true. It depends upon the boundary conditions. Do you include capacitance or do you exclude capacitance, et cetera, et cetera. And in the more general situation, the current can pick any wire and can divide itself among multiple wires, and it will do so in such a way to dissipate the least amount of heat. And so this is very surprising. It's not taught.
So are you saying that if you start with a system out of equilibrium, you just power it up?
Okay.
On the first moment, it's going to be using more power, and then the power use actually drops to an equilibrium state.
Right.
At a certain driving.
Yeah. Think of an inductor.
What?
Think of an inductor and a resistor.
Mm-hmm.
And let's say you put in parallel with the resistor, you put a capacitor. So there will be some kind of initial transient while the capacitor charges, but after a while it's just DC. You can't do anything. It's just DC, and you get the DC result. So in that way, if you allow for the possibility of transient currents, the current can go anywhere.
Mm-hmm.
But if you want steady state, you have to follow the laws of DC electricity. And that's one way to understand it. There are many other ways to understand it. But the reason I am bringing up this inequality.
I just want to say one thing. It's so people often use this analogy, or not analogy, but a type of idea that in general, life tries to dissipate more heat. I don't know if you've ever heard this kind of
Actually, I believe it's untrue. Life is very efficient.
Yeah.
And tries to generate as little disorder as possible.
Yeah, but there's it's very interesting because what you're saying, which sounds like it. I mean, I haven't read these papers, right? But obviously, they're probably mathematically correct. So because there's a concept in kind of like, I don't even know what science this is, but there's a concept in like ideas about what is life, what are the thermodynamics of life, that like life tries to increase. It's like, I think it's called maximum power.
Okay,
that life tries to increase the amount of power dissipated per second.
And the statement is correct, but it's the opposite. It's minimized.
Okay, that's very interesting.
Okay, now why am I bringing up these inequalities? Is because every inequality pushes you in one direction. It's the nature of an inequality. You get pushed in one direction. So suppose you're somebody in the modern world who wants to do optimization. Optimization is hard. Optimization can be done, but it's a very complicated math with a lot of linear algebra, and even optimization is needed for artificial intelligence. And so what is becoming recognized now is that machines, dissipated, which means every electric circuit, will automatically solve an optimization problem if you set them up correctly. And it doesn't have to be machines. It could be the principle of least action. Nobody actually uses that, but it could be. We don't know. There are other inequalities in physics that are potentially useful for solving hard computational problems. But here, thrown into our lap, is the simplest machines, circuits, and just do nothing. Let them evolve, and they will optimize something for you.
Analog
No, I would. No, I wouldn't. I would not call it analog, because people these days are not interested in analog answers. They're interested in digital answers. So the circuit can be set up bistable. So it applies to a bistable circuit, and then you get a digital answer. So it's very general. It's as general a property of physics as you could find, except that we overlook the fact that every equation, you can replace it with an inequality in physics. And so this, I think, is extremely meaningful. Now, in physics, there are only, at least in what's published, there are only two inequalities or two mechanisms that are used in physics. And one I mentioned is the principle of minimum heat generation. That's a sophisticated way of saying that, minimum entropy generation. The other physics principle that is used, that is published, is the adiabatic principle. And the adiabatic principle is sometimes put forward as a way of, as an algorithm, as a quantum algorithm. But the adiabatic principle works in quantum mechanics, also works in classical mechanics. So you have a company, well, I don't want to mention company names because they'll get mad at me, but there are claims that people have a quantum computer, but it doesn't look like a quantum computer.
Oh, the quantum annealing. That's the
quantum annealing. Yeah, quantum annealing is another word for the adiabatic principle. It doesn't have to be quantum; it can be classical, so those are the two that get published. Okay, and the people who do, even if they do classical adiabatic principle, they call it quantum annealing. They're all classical as far as I can. I haven't seen a single one that's actually quantum mechanical. Someday we might have quantum annealing, but up until now, it's the classical adiabatic principle that gets published. And so I wrote a paper 3 years ago analyzing everybody's scheme, and I showed that everybody's scheme that they're all very proud of reduces to following Onsager's principle. And I excluded the adiabatic principle when I did that analysis. So most of the papers are using the Onsager's principle, the principle that you should, they make a circuit, they make a machine. It could be mechanical, and the machine could be optical. And we analyzed them all. We wrote a paper, a very difficult paper to write, because we're analyzing 6 different experimentalists, each with a different notation, each using completely different physics, and each of them is using the principle of minimum heat generation, surprisingly. And of course, they were surprised because they all want to believe that their machine is different. Their machine is special. And I said, no, you're doing it. You could have done with a circuit. You didn't have to go to low temperatures, et cetera, et cetera. Yeah, because you're doing the same thing. You're fine. So typically, these analog solvers, they're solving the icing problem. Okay, that's very typical. But there are now some nice new publications solving problems in artificial intelligence. And so I think this is going to become a thing. There's going to be a conference on this at the Aspen Institute this winter. So it's kind of interesting. It's gradually, it's like used to be a few years ago. I've done something amazing. Congratulate me. I have this wonderful machine, and please don't change anything in my machine, because if you change it, it stops working. And someone has a different machine, they make the same claims. And they also want to claim, no, only my machine works. You cannot change anything.
So when we were preparing for this this interview, I watched, or I think we watched it together, a part of a lecture you gave about this topic.
Yeah.
And I don't think we didn't get deep enough into it to really understand it. Even now, I'm like still, my brain is a little broken from what you said. But there was a piece there where you also mentioned the optical, like the silicon photonics chips, where they've done some like. I think
from MIT, we have two versions of silicon photonic chips, completely different types of circuits, but both of them ending up solving the icing problem.
What does that mean in the Onsager? Am I correctly pronouncing it?
Yes.
How does that apply to an optical chip, like a silicon photonic circuit?
Oh, I see. You're asking how to specifically design the chip.
Well, no, the chips that they did, I think you included them as one of these systems that are all equivalent. They're all solving the same thing. How is that working?
There are two aspects to your question. One aspect is use the photonics chip to do optimization, which is perfectly fine. But then the other aspect is use optimization to design the geometry of the splitters and all the other things that are needed on the photonics chip. And both of them are perfectly good optimization problems.
Well, no. So my question is the following. So you mentioned how like an electrical circuit trends towards dissipating less heat at steady state when it's powered. So how does that work in optics? Like what does that translate to in an optical?
Okay, so I'll give you the example from MIT. They had an optical chip. It was basically doing unitary matrix operations, which you can do.
I actually worked a little bit with these chips myself. Like I've designed for totally different things. So I know all about these chips, and I can't figure out how do you map that.
Well,
so they have the matrix multiplier.
They have the matrix multiplier.
The mesh of MZIs.
Okay, and what happens then is they feed it back to the input.
Oh,
first you have to go through a little nonlinear element. There's no problem. They feed it's a matrix multiplier, so there are n outputs. There are quite a few outputs. Each one gets its own nonlinear saturator. Typically, it's some saturation thing, and then it gets fed back to the input. Now, because it's basically lossy, you have some gain along the way, and it goes round and round. Okay, and it converges. Because it has gain, it has loss, and it tries to minimize the total amount dissipated in the waveguides.
Really?
And that was an algorithm put forward. It's not that, there was one main paper from MIT, which was basically just using the matrix multiplier a conventional way in artificial intelligence. Okay, but then there was another.
By the way, that paper spawned two startups.
And both of them are failing.
Well, one funded. What the funny thing is, I know the story very well because I was at the time working on similar stuff. One funded by Google. I don't know if you know this story, but Google funded one, and that was the American. And there's a Chinese. I actually have met them both. They're both great, but the Chinese guy got funded by Baidu. And so there's like it's the two.
I understand they were both.
But the problem is that
they're both on Mass Avenue. And they're both inside each other, but they couldn't talk.
So the problem is that paper at the time, it still gets a lot of citations and everything, but that paper never showed that you could get an advantage. Like they were like, if we had a bunch of amazing things, this would have an advantage, and
it was kind of like that. And to the best of my understanding, they're both belly up now.
No, they're all doing transceivers. So basically, they got so much money.
Let me explain what happened. I was the advisor to a third company here in the Bay Area. And but they were all very headstrong because they were all sure that they had found some kind of golden thing, and it was going to be very successful. And I recognized at the very beginning that I kind of pulled away from it. I recognized at the beginning that moving data around is the whole problem in AI. It's not about the transistors, the logic, and nor even about the matrix multipliers, of which we have many kinds of matrix multipliers. It doesn't have to be optical. And that the data communications would be the main problem. That was actually the conclusion of my NSF center, which is, why do we have to make the transistors more sensitive? Well, because the biggest problem is communication. And if you want to communicate 10 microns on a chip, that's already a big deal. It costs a lot of energy. And so I knew that this would be the rate limiting step. And what happened, there were a number of companies that had really neat matrix multipliers, but that was not the issue. And they were told, so the reason they still exist is that their funders told them, yeah, the problem is data communication. Why don't you work on data communication and solve that problem? But then if they work on data communication, they run headlong into Luxtera, which is now owned by Cisco. And it's very hard to get an advantage in that field because that's an old field. The idea that you can do an optimizer, you can get it for free, and in a relatively simple physical machine. And so that has developed into a field. So that was my answer. What would you invest in? I would invest in that, but it's researchy. And it certainly falls into the category of Edison's 1,000 things that may not work out. It won't work out, actually.
I really like that. The photonic crystal was first a successful photonic
Right. That's right.
What does that mean? What is that?
Well, it's following the Edisonian method. Is that you
Are those chips, or what are they?
No, that is literally the first photonic crystal I ever made.
The first thing you made. Oh, that's
The first one I made. I thought I could get by with the refractive index of plexiglass, and it did not work out. But it's in keeping with the Edison's idea. You have to try many things. And after we were successful, I know some theorists said, "Oh, you could have done that by calculation." Actually, no, it's an optimization problem. It's very hard to do it by calculation. And the strategy of doing it by experiment turned out to be the successful strategy.
Yeah, it's overall looks very amazing that people try to show up everything that works, and then what doesn't work, it's hidden. So if someone else tries to understand
Yes.
what works, what doesn't work, you have to go through the same process.
So in my generation, there was a call for the Journal of Irreproducible Results. And because you have to also tell people what doesn't work. Don't waste your time. Maybe you learn more. You can write the theory why it doesn't work even. And so unfortunately, our society is not structured that way.
What's the if you were going to point to like one or two things that you think won't work that get a lot of people.
I will get people really mad at me. Okay.
But again, you've been wrong before, so it's not
okay.
It doesn't mean it's true.
I will just tell a story and you'll figure it out. So in 1979, I was looking to go into something. Energy was very important, and I had become interested in fusion energy. And I can tell you how I became interested in fusion energy. I went to the International Quantum Electronics Conference in 1972, which was in my hometown, which is Montreal. And the plenary lecturer was Edward Teller. Yes, the Edward Teller who created the H-bomb. And he was there to promote laser fusion. Okay, and I got the bug. And so I started doing research on laser plasmas and so forth. And I became rather disillusioned because I am more of a systems thinker, and I realized it's not going to work out. Okay. And the reason it's not going to work out is to make this work, the machine has to be very big. It will have a huge capital cost, and capital cost matters except to Marxists. For everybody else, capital cost matters. So I guess.
Yeah, there was recently this big result with laser fusion, but the wall plug efficiency of the laser is very low.
Yeah, it's
That's
saying the same thing. The capital cost of the laser is going to be ridiculously high, and everything's going to have to be extremely large, et cetera, et cetera. So,
are there any other approaches to fusion that you
there are
think
many,
are
no, there are many approaches, but I'll mention an incident that happened at that time. So I'm trying to decide what to do, and I decided to go into solar. And part of the reason I went into solar, it was simple, and you could charge a lot of money for the electricity. Okay, and whereas a lot of other things, you just get heat, and then there's a lot of capital costs converting the heat to electricity, and so on. So I decided but I was undecided. I was undecided at that time, and there were a series of articles written in Science magazine, and they said, look, there's these problems in fusion, and the fusion obviously works on a bomb, but to do it for civilian power, you have all these problems and so forth. And I think they mentioned cost, which is sort of the same thing as saying it required too much capital. But it wasn't just one article. It was one of the reporters, was a very smart reporter. He wrote a series of 4 articles, and he tore it apart. And I said, well, I don't have to be the one to tell them, because it's written right here in a famous, important magazine, Science magazine. Okay, I don't have to be the bad guy to tell them it's not going to work. And and I was pretty convinced, okay, that's sort of the end of funding for that. And what happened is then all the leaders of the plasma physics field wrote a letter to the editor saying, no, we are doing pure science, and we're going to continue, and et cetera, et cetera. And it did not address the points made and hid behind science, I would say. So it was, in other words, they did not answer the points raised in those articles. And I thought, oh, well, who knows what's going to happen. 5 years later, they're still funded. And it's now 45 years later, they're still funded, in spite of the fact that good articles were written explaining why it was not going to work out, at least for civilian uses.
This is fusion in general, or fusion's one specific approach?
The idea of making economical power. So once you get into business, you realize you have to go very far. At MIT, you go to Sloan School. It's right across the street from where you are, right? And you learn right away. Almost everything is determined by capital cost. Okay, capital cost is the most important cost that needs to be considered. And because you're trying to have a long lifetime, what's killing fusion is you need to keep the nuclei around for a very long time. The way you keep them around for a long time is you make the diffusion length very long. So you make a huge machine. If you make a huge machine, so how does it scale? The diffusion time scales as the square of the length. So there's a strong motivation, because you need long diffusion time so that they will stay together long enough to get enough power after you've invested it in compressing them. And so it's all physics at the end of the day. You end up with always a larger machine than you expected, much bigger. Usually in capital equipment, you say, how big is your machine? How many meters? Or if it's a ship, how many meters cubed? Okay, and that determines the cost. So you start with this tremendous burden, but nobody who's a real physicist worries about this stuff. But you have to be a little bit more of somebody who's a systems guy and thinks about all the different aspects, including what the capital cost is, how are you going to pay back the capital cost, what the interest rates are, and so forth, and what do the customers really want. And the customers want small incremental bits of energy. And so I knew at that time that I was leaving that behind. One of my unsuccessful forays into science, that I was, so before people got excited about optical plasma physics, I had already knew all about plasma physics, taught a course on plasma physics twice at Harvard. So I knew all about plasma physics. I had to put all that knowledge away, switch.
I actually have a question. So I think because you started your career basically in the 70s, right? So there's this period that I think went on while you were working, but also before you, where there was like huge progress in the physical world. So they were building tons of nuclear reactors, highways. I mean, you could list this out. And then I guess closer to now, we've had the build out of the internet, satellites, and so on. But it definitely feels, I don't know, at least to me, and I think a lot of people, that the 20th century was better at building large physical things.
Well, that's because you're too close to it. You see, you have to speak to an old person like myself.
Okay.
You're going to look back at Elon Musk's low Earth orbit internet.
Right.
And say, can you believe they didn't have that back in those days? That's what your kids are going to say.
But I guess
that's a big project, and it costs less than the interstate highway system.
But it's interesting that the only place you can do a big project is like the frontier, it's space, right? So for example, we watched this talk you gave recently on burying biomass, right?
Yes.
And it's, you basically went and calculated, I think it's like a pretty simple back of the envelope calculation that tells you that maybe with like 1% of GDP, you could bury enough biomass every year. Now, there's a whole claim that it doesn't decay for thousands of years. So that's a big discussion. But assuming that works, do we still have, like, how would you get done a project that requires 1% of GDP? That's the kind of thing that people used to do. I don't know if America, besides wars, I don't know if we have that kind of thing going on anymore.
It's a good question. I hope it doesn't require a war.
I mean, COVID probably ate up, 5% of
waste. Waste. A big thing comes along when you have a big challenge. People rise to the challenge. The nice thing about, for example, some of the things that were successful, you didn't have to have the whole thing at once. So, for example, if we're capturing CO2, we don't have to capture all the CO2 the first year. We can go progressively, a little bit slower. And the same with the interstate highway system. We didn't need the whole system at once. Every highway you built made things a little bit better. And so I think you're missing that. And the brilliance of Elon Musk, he didn't need to have all the satellites up there so he could start getting revenue. Okay, because then he without all the satellites being there, he could just concentrate on the people in remote locations. But think it through to its consequences. Once all the satellites are up there, will we really need fiber to the home? I'm not sure. Okay, and so that's why I'm saying your grandchildren will be thinking, they used to have this thing called fiber to the home. They're so stupid. Of course, we can do it all with low Earth orbit satellites. So I don't agree that we can't do big things. We just have to have big things that are tractable. So if you have one big crazy thing that the first one is already going to break the bank and the second one is going to be almost as expensive, then we can't do that. But if we start pulling carbon dioxide out of the air, for example, maybe you don't pull out all the carbon dioxide, but you pull out your own. You pull out your own carbon dioxide, and the cost is reasonable. That's the beginning of something.
Because it's definitely out of left field, like totally different problem. I guess it's somewhat related to the solar panels and energy systems problem.
Yes. And if you listen to the old talk, remember I give a lot of credit to Al Rose, who got me into this and told me one day, calculate the energy cost of gasoline in dollars per megajoule and energy cost of burning coal. Not corn in dollars per megajoule, and they're almost the same. Then you have to really respect agriculture, which I have since that moment.
Yeah, that's very interesting. So this is one we had prepared, but I think it's a very interesting one. So what can be improved in academia or broadly to make more Elis? How does society produce more people that can play in both areas like science, but also applications, things that people use, like you're saying, all over the world all the time?
I think it's starting to happen. It wouldn't necessarily produce more of me. There are other people who have far more higher accomplishments. But there is a missing link. And I mentioned systems analysis. Physicists should be great at that, but they're not encouraged to think this way. I think the change that is happening, this is a huge change. When I started my first company, I got into a big fight with UCLA over patents. And I said, this is crazy. They should love this. They should be happy. No. They're bureaucrats. And a patent is a threat. So why is a patent a threat? Because maybe they have to license it. Maybe they charge too little money. Maybe they charge too much money. In either case, they could be criticized.
So they didn't want to file, or they didn't want to
What they would do is they'd let the filing deadline pass to protect their own jobs, really.
That's fair.
And that has changed now. That has so drastically changed. Berkeley has at least 3 incubators around Berkeley. There's one at Lawrence Berkeley Lab. There's one down the hill a little bit. So there are multiple incubators. Every university realizes that they've got to have a footprint in entrepreneurship. Courses are being given. The donations are being given to develop these things. So I see it developing, definitely 100% developing, that we're going to see more encouragement of entrepreneurship in universities. And that's a prerequisite. And I felt that myself, also other people I know, it was a bit of an uphill struggle to get technology out of the university into the marketplace. And now they realize this is crazy. They shouldn't do that. And some universities were more progressive about this than others. I think Caltech deserves a lot of credit. They've always given great encouragement. But other private universities are more restrictive. Stanford is more restrictive. To the best of my understanding, MIT is more restrictive as well. And I hope this will change as they, by now, they should realize what a big advantage this is for the university. In education, it should be part of the education.
Yeah, I think one thing that's subtle, but I think, I find interesting is as we're interviewing people that were, especially when we're reading papers like from the 80s, for example, like really papers that turn out to be very important, they're short and simple papers.
Yeah.
And that's a trend that I think also maybe has like a negative impact on people actually doing something, is there are all these kind of bloated, very promotional pieces of work. And then also universities re-promote them. So universities now have like PR departments. Whereas, maybe that actually helps get the science out there, but it's also kind of causes people to optimize for the wrong thing. It's a very optics-focused environment. And I think, I don't know how to capture some of the magic from when people were just writing a couple pages to report, something.
Some things have changed for the worse. One of them, we already mentioned, it's not so easy to go back and forth from industry to university life.
Mm-hmm.
Back and forth. That's become very difficult. Closely related to this is the pressure on the young professors to publish in specific journals that don't necessarily have such great refereeing, in my opinion. So that's a second problem. The idea of to publish for perception rather than for reality. How will this be perceived?
Mm-hmm.
Okay. Yes, we're putting way too much pressure on the professors. They have to read the minds of the people who read it, and I say to myself, I want someone who is a total expert in this field to be able to read this. But I do have a reputation keeping things simple at the same time. But it's a problem. I'm greatly offended by this puffery, over dramatization of papers, making them to something that they're not. It's something I hope will go away, but I don't know how to make it go away. Yeah. I'm doing my best. I'm not the only one. I have received a suggestion from our proposal from a very important scientist at Intel. He's so furious at the low standard of papers that are heavily publicized in electronics. So he says, I want to have a new journal, and I don't know how it's done. It was going to be an online journal, and it was only going to be refereed by people who knew what the hell they were talking about. And maybe he had in mind just his colleagues at Intel. But yes, that's something that's needed, is to, you have to literally defeat some of the existing journals who have a business model. And the business model is, in my view, promoting this sort of intellectual disease where it doesn't matter what you've published; it matters how you're presenting it, and the refereeing is very superficial. It just has to look good. Terrible, terrible. And so his idea to defeat it with a new journal, and maybe that's the way to do it.
Yeah, that would be exciting.
Do you have anything else would you like to share in the podcast what we didn't cover?
Oh, anything we didn't cover? Well, we covered things I didn't expect to cover. I didn't expect the carbon sequestration to be covered. I think you've done a great service and a great job to the field with these interviews. I think it's wonderful for students, and I hope it influences a student not to believe what everybody says. And the paper gets published in a so-called important journal. No, that's not decisive either. Paper has to be very important scientifically, and not because people say so.
And ideally lead to a startup.
I think that's in our field. That's one way you can tell it was an important paper, because if it was just a bunch of ideas where there's no systems analysis, then of course you can't build a startup out of it. But to build a startup, you do need to do the systems analysis. You have to consider many factors, and in systems engineering, they include social factors. What's going on in society, that becomes a big thing also. And physicists are not supposed to be experts at that, but I think we're pretty good at that, and we can figure out what's happening in society. But that you have to take everything into account, and I think physicists can be very good at that.
Great. I think it's a great. Thank you for the podcast.
Yeah.
Okay.
Thank you very much.
Yeah, thanks for taking so much time to talk with us.